it was kind of hard. It was kind of hard to find, and again, if something broke, you didn't really know who to ask to get help with, and you weren't sure if you had something that was really good and it was going to last. And then there were other problems, like there might be namespace conflicts in two packages you wanted to use, and it was just, there was a lot of great software out there, but it wasn't easy to find and use and get help for, and it wasn't, from a facility standpoint, easy to find and support and all that stuff. So I really see E4S as a great opportunity to change all that. And so Mike and his team of everybody have just done an amazing job collecting a lot of software that's very important to the HPC community. I think the first thing they did was start creating things like SDKs, so that they would make sure that you had a package of software that you could use at the same time that didn't conflict with one another, and let you, which was a great first step to begin with. And it's really evolved since then, and now they collected this thing called E4S, and it's got a bunch of great software that's very useful to HPC. They've connected it with the developers, and they got the developers on board and worked out a way to support the software, ways to install the software, way to distribute the software. And that, I think, really is changing the way that both users and facilities interact with, support, and use software. And I'm hoping very much that they continue to be successful, and I'm hoping very much that they continue to be successful after the lifetime of ECP. And so one reason I think we're at a very important juncture for this is I really want Mike and company to really start letting people know what a great thing that they've put together here, and really get people to try it out and use it. And if something's not working the way they like, make it better. Talk to the team. They're very receptive to doing what works for users. And then I think it's really only with the users and the people of the facilities who support the software really wanting to use it and making a case for it. I think that's the strongest advocacy we have for getting funding and other things that are needed to support and continue to develop this software. So I'm really excited, and so I really urge you to have a good day and learn about E4S. Try using it. If something's not working, report it, because it's going to get fixed. We have a great chance to really influence the future and build kind of an HPC user software environment and set of tools and libraries that is sustainable and really changes the way that makes it easy for people to go forward, and gives them some confidence that the software they're using is going to be supported in the long term, and there's a way to get help and get bugs fixed and this sort of thing. So with that, I'll turn it over to Samir, I think is going to tell you more about what E4S really is.
Thank you, Richard. Let me share my screen, and my slides are located here. And here, I hope you are able to see my slides. Just a second.
Yes, that looks good.
Okay, so what is E4S? It is the extreme scale scientific software stack, which is a curated SPAC-based software distribution. I'll describe the different components of E4S, and these include binary build caches for bare metal installs. They can help speed up your installation of software, and it has build caches for x86-64, PPC-64LE, as well as AArch64 or the ARM platform. Now, we also have container images that are hosted on Docker Hub and on the E4S website of pre-built binaries, where we have base images and full-featured images with support for GPUs. We also have recipes so that you can start with something simple. You can start with a base image and then create your own custom image, and then create an image that works well for your applications. where a lot of the dependencies that your application may have are already supported by binaries that are pre-installed. We have support for GitLab integration, for building these images, a full validation test suite, so that we can check that the software is doing what it intends to do or what it has published. And also a container launch tool that allows you to substitute an MPI in the application built with the container. We have VirtualBox images, we have cloud images on AWS as well. So let me just recap. It's a SPAC-based software distribution, and it has been tested for interoperability and portability to several architectures with support from GPUs from 3 vendors. That's right, Intel, AMD, as well as NVIDIA GPUs are there in an E4S distribution, and it's available from source form, so you can build everything from a scratch if you wish, or you could speed it up using binary build caches that we have. We have support for containers, again, base and full-featured containers, as well as cloud images. And we use the SDK for interoperability, and it's an open system, starting with our first release in October 2018, where we had 24 full packages. Now we have over 100 full release products in E4S in our latest May 2022 release, and we'll be having a release next week for the 22.08. So we have an aggressive quarterly release schedule, as you can see, and we have support for HPC as well as AI components. We include support for PyTorch, TensorFlow, with builds for CUDA, with builds for ROCm, as well as other co-design packages like Amrex, Kibana, MFEM. So we use SPAC for the software delivery. And SPAC provides the ability to describe versions of different packages. And it allows the full software stack to be built. So it's the main platform that we use for delivery of the E4S products. You can find out more about SPAC from this web page. And the reason we use this is because scientific software, as you all know, is becoming extremely complex. And this is the dependency graph of NALU. Here we see Deal2, a C++ finite element library, and you can get the idea that the software is becoming really complex. This is for R minor. And even proprietary codes are often based on many open source libraries. So we are building an entire ecosystem of applications, packages on different platforms with compilers, programming models, and different versions of each package and external dependencies. And this leads to a combinatorial explosion. And every application has its own set of dependencies. It's become so complex that sometimes we see that centers are dedicating several FTEs to just building and porting of applications that often trade reuse and usability for performance. So we must make it easier to rely on other people's software. And a naive approach is to just download all the tarballs that you need and start building them one at a time, where we essentially fight with the compilers, tweak the flags, and finally, when we build all the packages that we need, we try to integrate it into the binary and run the code. And when it seg faults, we start all over again. And you may say, what about modules? Well, modules are just environment modules that edit your path, your LD library path, and they rely on somebody else having installed the package. So how do we use SPAC? SPAC is a flexible package manager. You can just git clone the SPAC repo and source the setup env.sh file. That's the first stage. And then you can install a package. You could say SPAC install tau, and then tau and all its dependencies are installed. I'll also recommend that you do a SPAC compiler find, so it will just pick up your own system compilers, so you don't have to start from a scratch and build compilers, and external find, so it can find packages like M4, AutoConf, and such packages that are already installed on the system. And then you can say SPAC install tau, but you can say SPAC install tau version 2.31 for a custom version with a GCC compiler specified with the percentage, and a @ symbol is used for the version. And you can then specify a plus ROCm build option or MPI options like this, where you can specify dependencies. And then you can say spec find, and it will show you all the packages that are installed, all the specs for a given compiler and version. So in short, SPAC simplifies HPC software installation and is the platform that we are using. And it enables software reuse for developers and users. It allows the facilities to consume the entire ECP stack. And you can learn more about it at this web page. Now, we have deployed E4S on many different DOE systems. Here is a dashboard where we can go to dashboard.e4s.io to see exactly which directories and where it is installed. We even have the results of the test suite or the spec.yaml recipe, which was used to build on that system, and how to use the modules or how to use the spec.yaml over here for all the different platforms. And you can see Perlmutter represented over here. And I'll talk a little bit more about how it is installed on Perlmutter. So on Perlmutter, we can use the progenv GNU, and you can just say module use this module files. You can say module avail E4S and then load this progenv GNU, and then you can see the packages. If you wanted to see the listing of just those packages that have support for the A100 GPU, the Ampere architecture, you could say spec find plus CUDA, and then it will list that. But then you could say where the CUDA arch is 80, and then it will list all of these packages. And you can see other packages like NVHPC, and then load some of these. But which packages do we have? This is the installation with the Slurm and GCC aware MPI from MVAPIC2. And you can see all of the packages over here that are installed on Perlmutter in these directories. And you can see there's a list of 74 packages here. And with progenv GNU, you can see another listing with 81 of these packages. So tools like sundials, like PETSI, Trilinos, Raja, these are important tools to have in the software stack. And they are all pre-installed using these packages in the directory, as I showed. What is interesting is that you can also have SPAC in your own home directory, in your own packages, and you can daisy chain the packages provided by SPAC from E4S with your own packages so that you can get a full union of the full set of packages. If you are interested in looking at the containers, you can download them from the E4S.io webpage, and it has a download section here. You can get the Singularity containers which support CUDA. You can look at the IBM PPC64LE with CUDA. We have base images as well as full-featured images. And if you're wondering about containers, well, containers provide a lightweight collection of executable software where you can nail down the dependencies, and you can have everything that is needed to run a single specific task without the overhead of an operating system kernel. It's based on Linux, and you can distinguish it from type 1 and 2 hypervisors where you have two sets of operating system kernels running in the case of type 2 hypervisor, and VMs. So in this case, there are no VMs. There is no separate operating system. It uses the kernel of the host operating system in a container. And it's a lot leaner. It's easier to use. And you can just use a Docker command like docker pull ECP E4S and download the images on, say, your laptop, and you can get the full environment. And you can see the full-featured GPU images here for AMD, for NVIDIA GPUs and Intel GPUs. So we have separate images with the Singularity image format files with these directories. And you can also get them directly from Docker Hub, like I have shown here. But it's not enough to just make a full-featured container. We also have GPU base images so that you could start from a scratch, make a custom container that is very compact, that has the runtime for the 3 different GPU architectures. So you'll likely use only one of them at a time, but you can start with a base image like this for ROCm or CUDA, and then build upon that with your own recipe. So you could use a from statement and refer to this image in a Docker file. Here is a base image again for the SPAC base image of E4S, and you can see that we've got over 1 million downloads of this image from Docker Hub. So it has been widely adopted by the Linux community and not just the HPC users. And this is the list of packages that are available in the container image, the full-featured container image. And you can see over here all the packages, including packages like Pappy or Magma or Cocos or Tau and Trilinos with support for different runtimes. Now, if you want to use a container on Perlmutter, we recommend using Shifter, and then you can just specify the image name. You don't need to download it because it's already downloaded for all the users. So you can just say the image is the ECP E4S base CUDA for a base image, and then you can specify the bin bash with the startup file, and you can see that it can access the A100 GPU and see the bare minimum set of packages that are installed with MPI, with CMake, with just the CUDA runtime library. And if you want to use the full-featured image, you can just say, Shifter IMG images and look at the 22.05 image and specify that image in Shifter command like this. And again, here is an example of showing you all the packages that are built with the A100 support. You can also use the AI ML stack right of the container, and it will have support for the GPUs. So I say import TensorFlow and list the physical GPUs. It shows me the GPU 0, which is of the type A100. And this is for PyTorch, where I import Torch, and I can say, give me the device name, and you can see the A100 PCIe 40 GB on the login nodes. And then you can see the list of all the CUDA packages for architecture 80 and 70. So in the same image, we have support for V100s as well as A100. We also have support for GUI tools. We have ParaView, Visit, Paraprof from Tau. These are all tools that support 3D graphics. And also you can use newer languages like Julia. You just load the module and launch Julia like this. And here we see the output from NVIDIA SMI, where we see the GPUs. Now, if you want to create your own environment, you can do that by starting with one of the recipes that we provide in that spac.yaml file, and then you can tweak that recipe. So for example, if we have all of these packages in the installation of Trilinos, you could change the list of packages. You could modify this SPAC recipe so that you just have what you need and not everything that's included in the E4S distribution. So it's a customizable solution. And here are examples of how we are using the CUDA specs for bare metal install. And you can build everything from a scratch on the target platform, or just customize this to create your own stack. Now we have an installation, as I showed on Perlmutter, which you could just use directly and then use your own SPAC and daisy chain both of those installations and access it. You can also verify that the package is correctly installed by looking at the results of the validation test suite. This is available on the dashboard.e4s.io, as well as you can look at just cloning this repo from this URL and then just launching the specific example. Like if you were using Magma, we have setup.sh, clean.sh, compile.sh, and run.sh script that can be used to launch multi-MPI rank executions. Here is an example of running the tests on multiple nodes using build test framework that Shazeb will refer to at NERSC. And we are using the CI/CD infrastructure using GitLab. And with the help of build test, we are able to launch the OSU micro benchmarks, for instance, where we can check that we are getting good latency between the nodes like this using the target MPI. And we are running some tests overnight with Trilinos and making sure that the libraries are correctly installed, they are running across multiple nodes, and you can use them. Here are the Docker recipes for multiple platforms, and you can see this is a Docker file where we say, start from this image. Now, this could be a base image provided by ECP E4S, and then you specify your working directory. You can copy the spec.yaml file and then change that in your own way to create a custom image where you can then install using SPAC, and then we have the support for build caches already in the base images. So you will be able to get a speed up where you can download the packages that are needed and then create your own custom images. Here are some Docker recipes for different architectures on Docker Hub, on GitHub. And then we have used it to speed up the installation of tools. Here are some examples with the WDM app, and then the Pantheon application over here. More recently, we are working with the Nalu Wind application in ExaWind and ExaSGD as well. And it gets sped up by using this build cache. Now, at the University of Oregon, we have hosted this build cache where you can just say, add this mirror to your SPAC, where this is cache.e4s.io, and then you immediately get access to over 88,000 binaries across different operating systems and different processor architectures. And then you can just download a package in a binary form if your compiler and your operating system match what is available in the build cache. So here is an example of just using Amrex, say version 22.05 from the build cache. And we are using this to create, images for ExaWind, where we create an image every night. And so we push this custom compact image to Docker Hub. And then if there is a problem in the code, they could go and check out an image which was created, say, on 19th of July, and then compare it with an image that was created on 18th. And if they find a problem, they can then find out what was working when. And so they have a complete list of all of these images that you can see over here in the ExaWind snapshot repository of ECP E4S. And we have a tool called E4S CL. It is a tool to help simplify the launch of MPI jobs that are using packages in the E4S containers. And we use internally the MPitch ABI as well as the V4 MPI layer from CEA in France for substituting the MPIs. And we support both MPitch variants such as Cray MPitch or Intel MPI or MVAPitch2, or we also support OpenMPI. So you can take a same binary and then you can create it with an E4S container and then go to another system and use the E4S CL tool to help launch it with the native MPI that is there on the system. So you can get really good bandwidth between the nodes of the HPC system because it's using the same system provided MPI. And you can essentially attempt to use the same binary with no changes, just with the help of the E4S container and the E4S CL tool. And you may wonder, how does that work? Well, you first get the MPI in your path. In this case, I'm using the one API Intel example. And then I just have to specify three things. In E4S CL, I initialize it with three arguments. The first is, what kind of container backend am I using? Is it Docker? Is it Singularity? Is it Shifter? I specify this container backend. I point to the image. I say the image is located here in this directory. And then there is a source.sh, which is the set of commands that you should execute when the container is brought up. Now, these commands could be very simple, like just enable the SPAC environment and then load up Trilinos with the support for CUDA, where the CUDA architecture is 80. So that it will load that Trilinos package and all its dependencies recursively. And then you can just launch it with the MPI run or srun command and just prefix it with the E4S CL. So just 3 things here. First, you load up your MPI in your path. You specify the 3 arguments here. And then you launch it using the srun or MPI run command. And it will figure out what libraries need to be bind mounted in the image and how it should tweak the LD library path to enable you to launch this. And we'll see an example of this in the hands-on session later today. And I'll show you a demo. Some of you can also follow along and try this example and see how this works on Perlmutter with multiple nodes. And here is the architecture of the E4S container launch tool. We also have a virtual box image with all of these runtimes. So you can use that to learn more about containers. And you can learn more about how we use the containers in the E4S project. We also have images that are running on AWS. Here is an example of an image where we have ParaView, we have ParaProf, and we've just loaded this example, which uses the Nalu wind test case. And we can see the detailed performance information using the Cocos profiling interface and see exactly where the time is being spent in the different solvers. This is again with no change to the binaries. So in case you're wondering what is E4S and what it is not, E4S is not a closed system that's just targeting DOE users, but it's an extensible open architecture software ecosystem that takes contributions from international partners, US teams, and it's not a monolithic take it or leave it software behemoth, but a full collection of compatible software capabilities where you can incrementally use the base components and build upon it to create your own selected components and create a custom solution for yourself. It's not a commercial product, but it's all open and it allows you to easily install software on your target hardware and use it with both bare metal and containerized distributions. I think of it as a conduit. It's a conduit for future leading edge HPC software targeting the scalable next generation computing platforms and a hierarchical software framework to enhance via SDKs the interoperability and quality expectations of our software. And I would like to thank the ECP project, the Exascale Computing Project, for their sponsorship of E4S. And I'll be happy to take any questions. We have a Google Doc set up here. Eric just sent the URL over here. Please feel free to ask questions there, even offline. And we have a Slack channel, the NERSC users Slack channel, where you can also direct questions and send the questions to the consult email as well. And we'll curate any issues that you may have on the use of E4S. Well, thank you very much.
Samir, question. How do you decide which applications you containerize versus which you leave running on bare metal?
Oh, that's a very good question. We work with the application developers to create custom containers. And so we can use the base images and then customize the list of dependencies that they need to create the complete set of custom containers like we have done for Nalu Wind. And we encourage collaboration with different teams, whether it is bare metal install using an installed E4S distribution or a containerized build of your application. We can help with both of those cases. Does that help answer your question?
Yes, thank you.
So here is an example. There's a question which says, I don't see broad compiler support in the spec. spec builds. So we do have several compilers that are supported. You can see on Crusher, for instance, we have the progenv GNU, progenv AMD, and progenv Cray. On the JLSE systems, we have support for one API. And you can see the results of the test suites and the entire SPAC-based installation using those containers. If NVHPC is of interest to you, we would like to make sure that progenv NVHPC is also supported on Perlmutter. I would like to have your contact information so that we can get in touch with you as we install it, so you can test it. And we would like to work with you on making sure that it has the packages that you're interested in, and that we support the program over there. And Richard, I assume that you have access to the access to Perlmutter, right? With the GPU nodes.
I'll let somebody that's more up to date. You mean currently today access?
Yes.
Shazab, I'll let you comment on that.
Yeah.
Following that much more closely.
Yeah, we do have access to GPU nodes.
No, I meant Richard Loft. Richard, do you have access to?
Oh,
Yeah, can you hear me?
Yes, I can hear you.
Yeah, rather than trying to type, because it's always awkward to do. It's like texting or something. So yeah, I have a kind of exploratory account on Perlmutter with some CPU node and GPU node access.
Great.
And our application is built dependent on OpenACC coverage and does not compile under the Cray compiler. So
Okay.
we need NVHPC in order to build the OpenACC.
And what is the name of your application?
It's basically the community Earth system model.
Earth system model. Okay. Well,
Yeah.
let's take it offline and let's work with your codes. Thank you.
Yeah.
So moving on, Mike.
Yeah, can you hear me?
Yes.
Great. Hello, everyone. I'm Mike Rue. I'm at Sandia National Labs, and I'm the Director of Software Technology for the US Exascale Computing Project. So you've heard some nice words from Richard Gerber and some nice details of how to use E4S from Samir. Today, I'd like to take a little bit of time, and there's more slides than I can cover today in any depth, but I'd like to leave the deck behind with you in case you have questions and want to follow on. But I'd like to talk a little bit about, I don't know, in some ways, how the sausage gets made, to use some kind of cliche about it. You know, how do we do our work? What's some of the value of the work, you know, from say a per product type basis, and how the portfolio is designed and our philosophy behind it, just to give you some sense of where we are and where we'd like to go with this activity. So anyway, that's what we're going to do. So I'll briefly talk about ECP. I want to talk about software ecosystems, and then a little bit about developing software for GPU systems. So ECP in a nutshell, ECP is a big project, 7 years or so. There are 3 focus areas: application, software, and hardware and integration. I lead the software technology area, and we contribute to about 70 unique products directly. And then, as you might have seen, the E4S contains more than 100 directly compiled products, and then all the dependencies that go along with those products. And so it's a pretty big portfolio, a lot of work going on. This is the leadership team associated with software technology. It's myself and Lois McInnes are the director and deputy director. And then There are what we call level 3 or L3 leads in the ECP lingo, Rajiv, Jeff, Sherry, Jim, Todd, and Catherine. And these are domain experts that coordinate a portfolio of what we call SDKs or software development kits. And they're experts in their area. They know not only their own efforts within the community, but a broad collection. They're very well aware of the solver library ecosystem, Sherry is, for example. And they coordinate activity across all the products that are being developed in their area. This is a leave behind slide of the technical areas. The only thing I'll mention is that NNSA, the far right column, is all of the libraries and tools that are developed at the NNSA labs that are open source or oriented. That's what it contains. Things like, for example, SPAC, Cocos, Raja. These are widely used open source products that are developed at the NNSA labs. These are Los Alamos, Livermore, and Sandia that need to be a part of the open ecosystem. So, and then all the other areas are organized by functionality. This is an eye chart, again, a leave behind of the leadership of the project at this time. There are 35 what we would call teams. You can think of as the development teams, like the Petsy Tau team, for example, the PAPI team for performance tools. These are the, where the real work of the project gets done. And these are just some stats. It's a big group of people. We're I think, pretty well organized, coordinating together as we get our work done. But again, just a sense of the scope of the activities going on. What do we produce? We produce a lot of things that you probably already use if you're in the HPC community. We contribute to 2 of the MPI variants, MPI-CH and OpenMPI. We do a lot of work in OpenMP and OpenACC, injecting new HPC features into the LLVM stack. We do a lot of work on performance portability libraries like Tau, for example, and then math libraries and IO and Viz and data. So these are the kinds of tools that we work on. Now, many of these are household names before ECP started, but things like Cocos, Raja, and SPAC were really not, unless you were really paying attention at the beginning. Now these tools have become commonplace in HPC. We're also involved in newer efforts that are still gathering momentum, like SICM, ZFP, and Unify CR. So this is the kind of work that we do. What's the legacy of this? Well, it's going to be a stack that enables performance portability on leadership platforms. And so many of you are presumably Perlmutter users or want to be, using NVIDIA GPUs and the nice deep software stack that they have. ECP is also investing in the AMD and Intel hardware and software stacks. One result will be is that you'll be able to write an application code that is portable to all 3 of those platforms, and while retaining sufficient performance portability and maybe having to specialize a few things that are specific to that particular platform. And you'll be prepared for new systems as they come along as well. So these are the systems we're engaging with right now, the 3, Frontier, Aurora, and El Capitan. And Perlmutter is a great system. We rely upon it heavily for a lot of our work and preparation for the Exascale platforms. I want to talk a little bit about the growing complexity of scientific application software stacks. Samir mentioned this already with a few examples. And this is a big challenge, right, that we face. And so this slide here just shows some stats from the Exascale project applications, roughly 30 teams, what they depend upon. And I think the key thing to look at is that the number of critical and important dependencies. So what this says is that on average, these 30 teams, their apps have a dependence on 12 ST software technology products. And roughly half of those are critical, or no, 12 of them are critical on average, and then 6 important. And then some of them have even a critical dependence on 40 of these. So this shows that the libraries and tools that are being developed in the ECP software technology portfolio are very important to a broad set of applications. And then as other applications start to use GPUs, the investment we've made for these applications can be more easily leveraged for new codes. Just a few examples of the kinds of activities that we have going on with these teams. COCOS is used within the Exascale application code, and they've been able to port from NVIDIA GPUs to AMD GPUs with really minimal effort. Audios is used by WDM app with a lot of success. These charts show some performance aspects. And then Hyper, which is an algebraic multigrid preconditioner package that enables scalable implicit solutions, is being used within the Exawin project. And again, seeing a big performance boost. So these are just some samplings of some of the successes. If you're interested in further stories, the application development portfolio produced this report. It's still in press, but there are quite a few integration success stories, meaning that ST, software technology, and co-design, which are another collection of libraries, have been able to integrate into the applications and improve performance and portability of those apps. So this is a sample of some of the products, again, revisiting, not to necessarily go deeply into them, but I want to highlight a few things. No two projects within the software technology portfolio are alike. You got MPI-CH and OpenMPI, just within those two MPI projects, very different cultures and very different, prioritization of activities. And then Raja and COCOS are two similar performance portability layers. Again, very different cultures and teams. SPAC is very important. All the math libraries, PETSI, Tau, Hyper, Trilinos, Flang, OpenMP, are part of the LLVM ecosystem. So you might ask, why, if you have all of these different types, what's the purpose of trying to bring them together? And I think that's an important question. In fact, all of these different attributes of these teams and products, why do we try to bring them together? And I think the reason why, and the reason going forward, is that each team is charged with challenging tasks. We need to provide capabilities for next generation leadership platforms. We need to address increasing software quality expectations. And we want to independently develop these things, but let's improve compatibility and complementarity as we go forward. And so really working together on these frontiers is better than going alone. And that's the answer to this. And we've already seen tremendous value from these efforts. So ECP's software ecosystem is truly a complex system, not just complicated. We have to plan, execute, track, assess, and repeat. And the challenges are emergent, right? We can see forward to all of the challenges there, and they're technical, sociological, and cognitive. And so it's to me, it's a fascinating aspect of ECP. I think of ECP as a big human experiment, which is what attracted me to the project to begin with. All right, so let's talk a little bit about, so that's a little bit of background on the ECP and the software technology portfolio. I want to talk a bit more now about software ecosystems via platforms. There's an interesting book by Nadia Eghbal. It's pretty new, Working in Public. And she talks about software platforms. And a platform is a digital environment that intends to improve the value, reduce the cost, and accelerate the progress of the people and teams who use them. And so it's in a sense getting better, faster, cheaper, all three. If you've heard the better, faster, cheaper, pick all three. Improving how people do their work can get you all three. And platforms are a very important part of E4S. And we have two of them. We have E4S itself, which is everything. And then we have these software development kits, SDKs, which are products of like type math libraries, IO libraries, each have their own SDK. And so I just want to highlight a little bit about what we're doing with those SDKs and E4S. So this is a hierarchical description of the three layers. The bottom layer is each individual product. You can think of a PETSI or a Trilinos or a Tau. And then we've been doing software that way for decades. Then the SDKs aggregate by similar types, community-oriented aggregation so that people can learn from each other. And then E4S sitting on top of all of that. E4S provides a lot of capabilities. I want to talk about just a few things and why they're important. So these kind of 9 areas: policies, doc portal, portfolio testing, curated collection, releases, build caches, providing a turnkey stack. These are some of the high level aspects. I want to talk a little bit about the community policies and doc portal, just to give you a sense of some of the value add that we get by bringing things together under E4S. I'll first mention the doc portal. So Richard mentioned already a little bit about, how do we get access to information about these products? One of the early requests we had from the facilities was, can you give us a place to go to find out about all these products? And so that was the impetus for creating the doc portal. If you go to e4s.io, just that simple string, and then click on doc portal, you'll be able to see the summary table that's here, that provides a brief description of all the products that are in E4S. It's searchable, so if you want to look for a specific thing by functionality or name, you can. You can sort by any of the categories across the top. And then from the development teams, all we need in order to populate this table with information about their product is the direct repo URL to the repository. And then we scan it for the meta information like the README file, the license file, and so on. And then we render this on a daily basis, this content. So as long as the repository information is up to date, all of this information is up to date too. If you like a product, for example, Audius 2, for example, you click on it, you get some of this rendered summary information that was just updated the day before. And then if you want more detail, you can click on the main link, and then you go directly to the Audius documentation page. So through this one portal, you get access to the documentation for all the products that are in E4S. The next thing I want to highlight is our community policies. And again, this is what we're trying to do with E4S, is not just package existing products and functionality together, but also incentivize and reward our development teams for doing a better job of scientific software development. And this collection of policies, which were defined and agreed upon by the E4S development teams, is a way of driving quality improvement. And so these 9 policies have been instrumental in setting a signal for how can we improve our software in ways that are meaningful to the users. And you can find this by going to e4s.io and clicking on policies. So one of the cool things about this is that back in December, we told our teams, okay, we want to assess your gap relative to these policies. Just, don't change anything. We just want to see, where are you relative to the policies? And the moment we said, hey, we want to assess gaps, a bunch of teams started looking at the policies, 9 of them, and then a bunch of them said, we can knock off a few of these with a little bit of work. And we started to see a big influx in pull requests to the testing repo for E4S from all of these different teams. And this is just a small snapshot of the bunch that came in. And so we see with these policies that actually the product quality is improving, even though we didn't ask for it. So this is the kind of behavior that we really like to see in E4S, and will overall improve the quality of software that you folks want to use and make it better and easier, cheaper, and faster. This is a leave behind slide of all the things that we foresee as values from E4S and SDKs in all of these different ways. So talking a little bit about expanding the value of the impact of software ecosystems going forward. I want to show 3 slides that show our business models prior to ECP or E4S, then the first version with E4S, and then the second version with E4S. So prior to E4S, if you were a user of libraries and tools developed at the DOE labs, you generally tended to use libraries and tools that were at the facility that you were working with, because you could trace a path from that facility to the scientists who were at that lab, and the facilities folks knew who to talk to at the lab. And so that it's not a universal statement, but there was this tendency to be local. because that's what you knew and that's what you could trust because you could contact people like that. And so there wasn't as much reuse across labs and facilities as there could be. And if you were someone in industry or say at NOAA or NASA or DOD, not a lot of hope to get good support from the facilities, again, except for that one facility that you might be going to. So what did E4S provide? Well, it provided an aggregation point for all the libraries and tools funded by ECP, but also others as we go on that allow, if you're a user at one facility now, you have a way to contact and use software from developed at other labs and available at other facilities at any facility and get the support through the doc portal and through an awareness of what's available. And so we expanded the scope. So now we can use things from all facilities and labs at any of the facilities and labs. We still didn't have a good answer for industry and other agencies. And so phase 2, what we've introduced now some 6 months ago or so, is the introduction of a commercial E4S support team. This team is then responsible for shepherding issues that occur with the use of E4S products. So if you're a user at the facility, you have a problem, your application is having trouble using a library, a tool that's part of E4S, the facility staff member will try to help you. And if they can, great. But if they can't, their next step is to contact the E4S support team. And they provide this tier 2 support for users. And it's their job to, first of all, look at the bug and see if it can fix it. And if they can't, to then identify the product team or teams that can help address the issue. And they hang on to that and run that issue all the way through to completion. Now, this kind of support is not only valuable to DOE users, it's also an opportunity to bring on other agencies and industry, because now you have a commercial company who understands E4S and can sell services to somebody outside of DOE and further improve the costs and benefit sharing of E4S. So this just summarizes essentially what I said, saying basically that we've gone from local cost benefit sharing to universal cost benefit and sharing, and that's a lot of value. And our stakeholders see the value in that. In fact, if you look at the latest CHIPS and Science Act, there's paragraphs in that act that talk about sustaining the exascale software stack. And I think a lot of the value from that is the value that we've been able to show during the time of ECP. And so we hope that that will lead to ongoing and sustained funding for our activities. I'm going to skip over this part because I'm running out of time, but I do want to say a little bit that we're not just doing status quo. We're actually starting to look at the science of scientific software development and use. In other words, trying to use scientific approaches to understand how people develop and use software to do research. We did a workshop back in December. We're putting the workshop report together, and we anticipate, if things go as we expect, to receive funding in sometime in the future to look at how can we better improve development and use of software using a scientific approach to that improvement. And again, this is just some leave behind stuff. Okay, so expanding the future. So again, we're not just trying to create a collection of software, we're actually trying to advance the state of the art and how we do scientific software as we go forward in the future. Okay, last few slides here. Developing software for GPU systems. If you've been tracking GPU systems, you know that we've gone from a CPU only under MPI to a CPU to GPU where you offload the performance intensive parts to the GPU, then multi-GPU where you have even more offload possible. But now we're to this point where really everything has to be GPU resident. All the bandwidth, all the performance is on the GPU, and we have multiple GPU types. And so that's our focus with ECP. Within ECP, there are two products, Cocos and Raja, that allow you to express things like basically loops in a performance portable way. And so a lot of our codes have adopted Cocos and Raja as their means of getting portability. What Cocos and Raja do is they allow you to write source code one time and then compile two different backends. And in fact, they even cooperate on some of the back-end work across these two libraries. Certainly you can use OpenMP, but with GPUs, the target offload stuff is still maturing. And you can use vendor-specific things like CUDA and HIP, which is very similar to CUDA, and SYCL. But generally, we found that people like to use a blend of Cocos and Raja and specialize just some kernels down to the vendor-specific CUDA, HIP, and SYCL. I'll just mention briefly what we call a co-opetition model that we use. Then what this does is allows us to explore new design spaces within our SDK. So this is the Math Libraries SDK. And one of the themes to extract parallelism from our applications is to use what are called batched computations, batch linear algebra, batch solvers. This allows you to express lots and lots of independent activities, tasks that can go on, and then throw them onto the GPU and let the scheduler on the GPU process them and do so in a balanced and high performance way. Our libraries teams, our math libraries teams, try to explore that. And then they've also been looking at low precision arithmetic as part of that. And exploring this design space together, they run a bunch of different workshops, and each speaker from a different team will come and talk about what they've learned about various aspects of using low precision and batch computations, and they would share that knowledge together in an open way. And then once they've discovered, okay, this is the design space, these are the design trade-offs, each library team was able to go and invest then this known knowledge they had into the specifics of their library. So we call it co-opetition because they cooperate in the design exploration phase, but then they compete by taking that knowledge that they gained and injecting it into each of their libraries. We view this as a really nice way of balancing the ability to share and to also create products that are distinct. Okay, just a few more words and then I'll end up. So some early access system experience, very high level, but I just wanted to show you a few things that we see as patterns. One is performance portability. So this is just the math libraries area, but it kind of shows what's going on elsewhere too. There's one strategy where people try to isolate every single performance impacting kernel and then write their own CUDA, their own HIP, and their own SYCL implementation, and then whatever else would come along of a vendor-specific type backend. A second strategy is to use something like Cocos and Raja as your primary portability layers, but then you can blend those two, and this is what I mentioned, where you can blend two of them and do everything in Cocos or in Raja, and then if you have something that's not performing well enough, you specialize it to a CUDA, HIP, and SYCL version, so you can get that last little bit of performance out of things. And so the only thing I want to mention is we do not use OpenMP directly within the math libraries. It is used behind Cocos and Raja. Okay, last comments. I want to show, just to describe to you briefly, the sense of what is sometimes we call the E4S two-step. And step one is if you have an existing MPI plus CPU code, you want to build it on top of E4S. You can do that even though you're not necessarily using GPUs right away. All of the E4S software, it builds for MPI plus CPU, or even a laptop for that matter. And so you could do, if you wanted to start using E4S, even though you're not using GPUs, just start trying to utilize it. Samir and his team are very ready to help you to get started and launch you. And then what you can do if you stabilize on top of E4S is then the second step is to start turning on the GPU builds. Start using the GPU features that are part of these libraries and tools. And we think that that is a reasonable way of splitting the complexity into two parts as we try to adopt to GPU platforms. All right, so just a little bit of a summary, again, a leave behind. And then the last summary slide is, using this portfolio approach that E4S and the SDKs provide is really about going together versus going alone as a collection of developers, because we face these same frontiers, these evolving demands and systems. All of this software is available from leadership to laptop computers. And these new platforms of E4S and SDK, I think, enable better, faster, and cheaper in-net. Yes, there's cost to being part of an SDK, cost to being part of E4S, but the benefits are so large, I think those costs are easily overset or overcome. Having a E4S allows some new relationships with the facilities, with vendors, with apps, with industries, and we're talking with other US agencies. We had some great success with NOAA recently on the ability to use E4S for new simulations and greatly reduce build times. And just I list here a few things that NERSC users could benefit from as we go forward, and I'll stop here. Thank you.
So
Okay.
Mike, you have a question in the
Yeah,
Google
let me look
Docs.
here. Okay. Okay, I see. Hi, Marta. Let's see, was commercial E4S team. Let's see.
Mike.
Samir, maybe you want to take that one? I think that's, you can give an answer, right?
So I'm looking at the question. What is the package policy for an
No,
E4S?
one question above.
Okay. What is the way to get in touch with the commercial E4S team? So right now, the best way is to just reach out to me and we can go from there. So let me just say reach. And we can take this offline and see how much, what platforms you're interested in and what kind of support you would need. Thanks.
So question 6 is, each package team, the only signal we have for whether or not to update a project in E4S is that the spec recipe submitted for E4S has changed, right, Samir?
Yes.
Yeah, and so it's very minimal, but it's working for us so far. I foresee as we go forward in time that we will introduce some more rigor and formality to what we're doing. The ways that we make sure of things, but as we're bootstrapping, the approach we're using is informal but effective. All right, thank you.
Shazeb, did you want me to go next, or did you have some
Yes.
logistics you wanted to announce?
No, you can go ahead. We'll do it after the break.
Okay, that sounds good. All right. Well, hi, everyone. I'm Katie Antipis. I'm the Director for Hardware and Integration for the ECP project. And I'm also the Division Deputy here at NERSC. So, I don't have all that many slides today. I think I've already seen a few ones that are repeated between that Samir and Mike and I've had. So I think I'll just run through these quickly, and then I can take any questions that the team has. Let me see. I think I'm in. You guys see full screen mode here?
Yes, that looks good.
Okay, cool. Right. So I think Mike sort of covered this here. You can really think of it as 3 pillars in the ECP project. Mike and Lois McGinnis lead the software technologies pillar. Andrew Siegel and Eric Dreger lead the applications development pillar. And then the third pillar is really hardware and integration. And so what we do in hardware integration, just in kind of a nutshell, is that we take the applications and the software that are developed in these other two pillars, and we make sure that they work in practice at the facilities. And so in a lot of ways, we call ourselves hardware and integration is the glue or the last mile that really allows us to capitalize on the investments that have been made. You know, it's great if all of these products and applications are developed, but we want to make sure that they actually can run on the exascale and pre-exascale systems. So that's our focus in hardware and integration. And we work in a number of different areas. The topic today, of course, is software deployment, and specifically in E4S and how that will run on the facilities. In hardware and integration, we also work on in some other areas as well. One is application integration that I mentioned. So we help application teams get their applications ported, optimized, performing well on the facility systems. We, in hardware integration, put on a lot of the training activities and the productivity activities. In fact, this one is being run by Osni, who and Shazeb, who are you know, Osni leads the training area for ECP. And then we have a couple areas that have actually are kind of retiring and that were very prominent early in the ECP project, and that was in the hardware innovations and evaluations area. So that was the path forward area and hardware evaluation too. And so, you know, I think I just summarized our different areas here. And again, we'll focus today more on this software deployment area, but I'm not going to go too deeply into it because you also have a talk from Ryan Adamson a little later today. So here is our team. My co-lead in this effort is Susan Coughlin, who is the project director for the Aurora system. And so we work together closely every day. And then we're in the midst of, I call it a Ryan to Ryan transition, from Ryan Adamson to Ryan Prout. Both are at OLCF. And so Ryan Adamson has been the L3 lead for software deployment for, I think, about 3 years now, 2.5, 3 years. And Ryan Prout is taking over. So we're really happy to have him on the team too. And this gives you a little sense of our org chart and our position within the ECP project. So Ryan, I can just say Ryan Prout leads the software and deployment area. And then there are 3 columns or level 3 areas or level 4 areas, excuse me, under him. And so one is around software integration. That's actually led by Shazeb, and that's about getting the software deployed onto the facility's hardware. The next area is continuous integration. And I think of continuous integration as how do you automate the testing and deployment infrastructure? So you could integrate things all by hand and make them work, but then how do you make sure that this is done, you know, on whatever frequency that you want in kind of an automated way. And then sort of separate from the activities we're talking about today is a slingshot testing area that Jay Srinivasan leads. And so in the next year, what will we be doing for hardware and integration? Well, this is where, I mean, I think we're at the point where the rubber is meeting the road. The Frontier system is deployed at Oak Ridge. We saw they got an HPL number for the June top 500 run, which was awesome. And they're in the process of acceptance testing for the system. And so we expect that ECP users will be able to get on the system in full in the next month or so. There's a few teams that have early access that are on right now. Perlmutter, as you know, is on the floor, and we're expecting Aurora to be on the floor next year. So we're really in this phase now where applications are getting on this test system. So there is a test system for Frontier that looks exactly the same as Frontier, except it's just a single cabinet. It's called Crusher. And so our software deployment teams and the software technology teams, the application development teams, all have access to that hardware. They all have access to Perlmutter too. And we are in the process of debugging these systems, filing bugs, testing our support model as these systems come online. Okay, so I wanted to take a quick step back and talk about, I would say it's a major accomplishment that Ryan Adamson led us through a few years back. And one of the big things we were trying to figure out is software technologies has 71 products. How in the world are we going to get these deployed onto the facility? Are we going to be dealing with, I'm talking as a facility person, are we at the facilities going to be trying to talk to 71 different PIs to get support and issues? And it didn't seem very manageable. And I would say no one really had a good plan or vision for this. And I think Ryan Adamson came into the position a couple of years ago, and he looked at how the teams were building SDKs and E4S, and he says, this really, we can leverage this. And if we deploy this as a package, then the facilities can interact with the E4S team, and then the E4S team can individually communicate with the 71 other different PIs if they need help or support. And so this actually allowed us to make progress a lot more quickly than I think we ever would have. If you had seen our reviews from a few years back, one question is, how are you actually going to do this? And once we put forward this model to use E4S as our and SPAC as our deployment model, immediately we started to be able to make progress and get the software actually deployed on the system. So I think that was just a big strategic change that Ryan Adamson put through, and I think it's paying off right now. So I know Ryan will talk more about this. He's going to be better at talking about this than I am. But we have like a whole process for how we get this software actually deployed and built at the facilities. We have a development branch, we have a stable release branch. And so we're starting to make kind of our software management closer to, I think, what's done in industry or in the best practices in the world. And I think this is only going to make, as Richard Gerber said in the intro, I think this is only going to make our software stacks at the facilities, more robust. Certainly something that all the facilities are thinking about now is what kind of software do we get from the vendors? What kind of software should we, the community, provide, and what's the distance between those? And I think we as an HPC community are probably going to have to step up and provide more of the software ourselves going forward. And E4S, I think, has a great place in that ecosystem. Okay, so I thought I would just give a little bit of a snapshot of how we actually did this, or not me, I didn't do anything, but how Ryan and the software deployment team really got this worked out with the facilities. So what they did is they laid out all of the ST products and tried to figure out what were those initial products that would be targeted for Frontier. This is an example on Frontier. And then what were some of the secondary products? And they were really looking at where were the kind of the largest number of dependencies. And so when we started this process, let's just say there was not check marks, right? There was about 5 or 6 check marks in terms of packages that were ready for deployment on Frontier. This means that they work on the Frontier AMD GPU hardware. They've been tested, they've been ported. And so slowly over a period of over a year, we've been able to get more and more of these software technology teams ready for the Frontier architecture. And so then as of, this was a couple months ago, the last, our quarterly report, we have just about all of the teams that we had initially targeted with access to the system. And when we don't, in this case, HPC Toolkit, I think is not quite ready yet. This could be because of system issues or other challenges, and we track those as well. Maybe one other thing to note is if you count all these up, there's not exactly 71. And this is because some of the products actually come sort of, I would say, in through a back door through the facilities software stack. And some of those are like MPI, for example, that we work on. We end up using the vendor software stack for that one. And then finally, I think my second to last slide here, I wanted to say a little bit more about the level 2 support plan. I think this is huge. From the facilities perspective, we can deploy E4S, but then there's a question on, well, what happens if we get questions about it? And so we came up with this agreement with ECP and the 3 Oscar facilities that we will have this level 2 support plan with the E4S team. And through the duration of the ECP project, this will be in place. And of course, we're looking for ways to sustain this past the ECP project. But what this means in practice is that our users, you will still submit a question or a ticket like you always do to the facilities. It's help@olsf.gov or the help desk at NERSC. And our facility staff will triage it because it may be an E4S issue, it may not be, right? There could be an issue with the system, and just because you're running a dependency with E4S does not mean it's an E4S issue. Our teams will troubleshoot it, and if they need additional help, then they can escalate that issue to the E4S team. There's certainly nothing that stops you as an end user from directly engaging with the E4S team. They have an open GitHub issues here if there's a particular feature or something you're looking at. But we expect that most of our users are used to submitting tickets to the facilities. That's the path they might most likely take. And so then we have a way to escalate them. We're tracking the time to resolution, the progress, user satisfaction. And so far it's been working quite well. And I've been really happy with kind of this model that we set up, and I hope we can demonstrate how this is working well for a model post ECP. And then this is a complicated diagram that shows where a ticket goes if there is a particular issue. And so I think that's all I have. I'll get us back on track. Timing wise, I'm happy to take any questions about where software deployment fits in the larger HI ecosystem, or any other questions.
There's 2 questions in the Google Docs. So
You want to read them for me? I don't think I have that one open.
I think they were for the previous talk.
The previous talk, okay.
For
Yeah.
Mike Carew. There was one that came up that maybe is also relevant to Samir. Question by Mark: is there an intention to include Python products in the curated software stack?
And yes, I'm happy to say that we do have support for Python in E4S, and you'll see more support for HDF5, including the Vol async package in the upcoming release. And we have NumPy, we have SciPy, we have even TensorFlow and PyTorch, all integrated with support for GPUs. So yes, we can work with you in validating those packages that you are interested in for Python, or you can also do a pip install with the user to install additional pip based packages in your directory.
Okay, Shazeb, so I think we'll hand it back to you here. I don't see any other questions.
There's a question for you, Kathy, on the Google
Yeah.
Doc.
Oh, there is. Okay. Someone want to read it out?
How do you see E4S support model scaling to the universal adopter as Richard was talking about?
Oh, wow. Okay. What is it? What do you mean the universal adopter? Like, scaling to the
Okay, so Richard was, the other Richard was saying that, you know, it's been focused mostly on DOE.
yeah.
And then there was this notion that it would expand to cross-agency users, like let's say an NSF scientist would go all in for E4S stuff. And then commercial and just, you know, anybody in the world would adopt this. But that seems to me to create a support issue of saying now somehow you have to expand your support framework beyond your level 2, whatever.
Right. So, and Mike can jump in here too. So right now,
yeah,
we have it. You go ahead. Yeah, go ahead, Mike. Why don't you go for it?
Yeah, sure. So we actually have a lot of conversation with NSF. In fact, I'm on the advisory committee for cyber infrastructure for the Office of Advanced Cyber Infrastructure at NSF. And so I talk a lot with Manish Parashar, who's the director, about strategies for NSF. In fact, we're setting up a series. We've had a few workshops. We're setting up a new series of workshops, you know, to engage with the NSF sites. I think we're going to start with NCSA because the Delta system there has a lot of, you know, variety flavors of NVIDIA GPUs, and I think one AMD, you know, probably for porting, right? And so we care a lot about that. And I mean, our ambition is to make this a kind of national software stack, in one way or another, so that, you know, if you're on a, you know, say a pretty standard HPC cluster at your university, you talk with your admin, get them to use SPAC if they don't already know how to use it, or set up the container environment on that platform, and that is readily available there. And then when you get to the larger facilities that have, you know, kind of leading edge hardware software stacks, we're going to be working with them, and making sure that the software is available for those systems. So does that help address the question?
Yeah, it does. It does for the cross-agency interaction. And I guess I was also thinking about this thread that kind of cropped up about commercial adoption of this, or a commercial ecosystem of consulting and support. And it just seems to me to be potentially a scaling issue, especially as everybody goes exascale. I mean, you know, we've seen a lot of presentations recently about, you know, machine learning, tailored machine learning systems, somewhat exotic systems being adopted, just the total growth in that area. So I'm just curious how you see yourself in that space.
Right. Well, you know, what we're trying to do is provide a lightweight but concrete step-by-step process for new capabilities as they come into the open source software ecosystem. You know, say a new product or new capabilities within an existing product, that there's as short a path as possible from that software being, you know, checked in and tested to being available through the E4S and SDK conduits that provide that. And the commercial aspect of it, this is an important element of bringing in Paratools as a commercial support team, is they already know the products in E4S, and as they support them for DOE and NOAA and NSF and other agencies, that knowledge base will grow, and that they can then also provide services to commercial partnerships. Every time we talk to the industry, we have an industry and agency council. Every time we talk to the you know, big companies, Boeing, GM, and GE, you know, they all want they want to use software, but they want to be able to call somebody or get support from somebody, and they're willing to pay for it. And so by setting up this commercial component to the software ecosystem, we enable that potential so that a commercial company could use E4S and pay a company to support them in the use of it. Now, you know, with all due respect to Paratools, our first commercial partner, I hope personally that there will be other, you know, scientific software companies who'd be also willing to you know, get into this model and start to support E4S and see it that they can provide a competitive, you know, business offering to support users of it. Anyway, maybe that's too much, but hopefully that gives you some sense.
I think we can take a break, or let's give a 10-minute break and come back at, I guess it's 1:40 Eastern time, Pacific time. That's 10:40. And then we'll resume our session. If you have any other questions, we'll monitor the Slack channel. Thanks. Session shortly. Second. Okay. So I just wanted to go a little bit on the logistics, since couldn't do it in the beginning of the session. So just a reminder, everyone's muted. You know, feel free to unmute if you want to ask your question, or you can even raise your hand and in Slack and speak. I think everyone has done a good job by changing their name, so I think we can see everyone's name, but for anyone that joins, just use your first and last name and you can rename it. There is a Google Docs for those of you that may have joined later. This is a link to the Q&A. We will upload the slides and the videos at the E4S training page. So also, if any of you that haven't joined the Slack channel, please, you know, send us your email. You can put it in the Zoom chat, and then you can send it to me directly or to Eric, and we will invite you. Just also a note, when you for the tutorial that will be coming up, you know, we encourage you to post your questions in the Slack. If you have any questions, just please reply in the thread, so that way it helps us to troubleshoot the issue. For those of you that don't have a NERSC account, we provide training accounts. So there is a link to this, you know, iris.nersc.gov, where it asks you to fill out a form, and there is a 4-letter code that you have to. If I just go over here, when you're filling it out, there will be four-digit code that you have to fill out. I think for the next step, right here, training code. So use this BK55, and then you'll get an account username and a password. So please save it, and you would use that to access Perlmutter. So I guess this is our proposed agenda. That's right now we're kind of a little bit behind schedule, but we're at the next talk, which is the NERSC back infrastructure. We're hoping that by the time we get to lunch, we can still proceed at 12:30 and hopefully finish within time. So let's get started. Okay, a second to roll my slides. Okay, so first I'm going to talk about the SPAC infrastructure project. I'll do a little demo, and then we'll talk about kind of how this works. So the project is actually available on our Git repository, which is contains all of the SPAC configuration used for deployment of E4S. And the way it works is that we have GitLab that automates the whole deployment of the E4S stack. And that's what you see when you go on Perlmutter or Cori, when you do modular load E4S. So the repository is set up in a way where if you want to know our SPAC configuration, we have a directory called SPAC configs with all of the directories, and it's pretty intuitive. So, it's the name of the system and then the version of E4S. So like, let's say the most recent one that we deployed was Perlmutter E4S 2205. And then you're going to see the SPAC.yaml configuration. That's the one that we deploy on our production system. So if you have any questions about how we do our deployment, all of this is readily available. For those of you that don't have access to software.NERSC, we also have a public-facing mirror of this on NERSC SPAC infrastructure on GitHub for the NERSC organization. And then, this is up to date, so you can look at it here. The next thing I want to show you is that we're going to be doing this for the tutorial. Is there's also documentation for this infrastructure. And for the tutorial, we'll do the SPAC training, but you can actually look at, for instance, all of our SPAC configuration in the docs. So you can navigate to, like, let's say E4S 2202, and you can see all of this here. And the intention is to make all of this publicly facing, so that anyone that has questions about the deployment, they can see from here. So let me go back to the project. So the way the project is set up is that we leverage GitLab to automate our deployments. So I'll go into schedules. So in CI/CD, we have different pipelines that are run at different schedules for the deployment. So on our system, we have Perlmutter and Cori. We also have our TDS system, Muller and Gertie. So the way you just run these is you can just press play on one of these pipelines. Let's just say I'm going to say Perlmutter, and it will trigger a job and start doing the deployment of, let's say, this Perlmutter E4S 2111. Now, this deployment is going to be done in an independent directory that is not going to be the production deployment. It will be in its unique directory that's wherever this job is being cloned. And, it could take several hours until it completes. So, yeah, this is going to take a little bit of time. I guess one thing I wanted to mention is, let's just say you want to look at one of our deployments. I guess, okay, yeah, let me do this. So for the pipelines, we also do the deployment of the production deployment. The way they work is that you have to, well, let me first talk about the pipelines. Every pipeline that we have, there is a unique identifier when we use pipeline_name that tells the which pipeline is run. So all of our deployment pipelines have a _deploy to differentiate between the deployment pipeline versus the one that is for just running on a scheduled pipeline. So in order to do that, you have to go, let's say, CI/CD, The only way you can trigger production pipeline is through the web interface. So we don't trigger pipelines on push or merge request or schedule event. The only way you can do it is you have to set pipeline name, and you set, let's say, Perlmutter E4S 2111 deploy, and then you run. Now, you might be thinking, well, what's going to happen? Well, first of all, we don't let the pipeline run automatically. What we do is we have a job that stages all of our deployments, and it requests for an approval. So that way you don't just have pipelines running automatically. Okay. So I'm not going to run this. I'm just going to cancel. So that's how this works. Let me go to the slide so I can find this. Okay. All right. So I'll be switching gears and now just talking a little bit more about the let me see if I can go. Yeah, let me download these slides. Okay. All right. So I'm not going to talk about SPAC and E4S. I think you already know that. I guess one thing I'll just mention is that, you know, E4S itself, it's a collection of SPAC packages. We get, I mean, right now it's like up to almost 100 packages, and you know they're built together. They're released every 3 months. And
Shazam, I can't see your slides if you have slides up right now. I'm not seeing them.
Oh, can you see now? I'm sharing the whole
Yes,
screen.
now I can see it now.
Okay, thank you. Okay, yeah, so E4S is released every 3 months, and what we do is when there's a release, we take what is available and then we try to build it. So the motivation behind this project was, well, previously we used to do all of our deployments manually on the terminal with, you know, just doing SPAC install of the whole stack, and that took a lot of time troubleshooting. So we needed a way to automate the whole deployment. So naturally, we just use GitLab because we have GitLab, and just let its CI/CD just do its thing and do the whole deployment, and then we can just come back and look at the results. The other problem is that, you know, the deployment process itself took a long time. You know, we're trying to build 100+ root specs. We wanted, it took about 4 to 6 weeks just to get the builds to complete. We wanted to cut it down to a week. Now, a lot of the times when you're going through these builds, you have to troubleshoot the build errors, let alone, you know, waiting on the terminal for the whole installation to complete. And it can take quite a bit of time. Just troubleshooting the errors until you get a whole deployment complete. So another problem that we had is previous deployments that we did, I would say prior to December of 2021, we had one repo per deployment, and it caused a lot of you know, different repositories, and there was no single centralized repo for all of our SPAC configuration. So that was a lot of confusion. So, and the other thing is that we also needed like GitLab runners to be able to run all of our deployments on all NERSC systems with a single user account. Previously, what we did is, you know, I would just go in, do our deployment with my user name, and that was it. So, so that introduces what the SPAC infrastructure project is. I'm going to skip this slide, but I'll go into the next one. So this is like a visual representation of the entire deployment process. And it's pretty clear how the process starts. The first thing that we do is we go to the GitHub project on E4S and get the spec.yaml. I know the output is a little small, so maybe let me do it a little bigger. How about that? And what we do is we take the spec.yaml and port it to our system. The thing that we're mostly interested in is the version of spec. Basically, it's a commit or a branch, and all of these specs that are provided by E4S. We have to obviously port all of our spec configurations, so that's all the compiler definitions, and then any package preference along with the specs that we want to install. Then we build the whole stack. So I kind of just showed you what it looks like. This is the production deployment where you press the approve and then it do the deployment. And if it's green, then hopefully everything works correctly. We generate the spec generated modules. Step 5 is what we have to do this manually, where we create a user-facing E4S module. And once this is available, typically users will see this and they will actually be using the E4S stack. While we're doing this work, we write the user documentation, so you will see a page per stack. And Eric is going to be talking about this in the next one on the E4S docs. We update the facility, the E4S documentation. So there's a facility dashboard that keeps track of all of the E4S deployments done by all of the facilities. We share a spec configuration. So I'm just sharing a pull request for one of our deployments. And then we announce it in our NERSC weekly email. And that usually concludes our entire deployment process. So for this project, as I mentioned, we needed GitLab runners to run the CI job as a user for our production. So we have a username that we used. It's called E4S, and we stood up runners for the different systems. So these are just the name of the runners that we have. And so if you want to run a job on Perlmutter, we would use this runner, Perlmutter E4S. Same thing with Corey, and then our TDS system. This is kind of what one of the deployment scripts look like. It's one thing I just want to mention is that we do all before we even do the spec build, we try to have as clean of an environment as you can. What that means is, since spec is a Python project, you need to have, like, let's say a virtual environment of, a Python virtual environment. So that way, your user environment, can be, your system user bin Python or some other Python, and that could cause a discrepancy. So we create a new virtual environment and we install Klingo because, spec needs Klingo, and sometimes I think this is still a problem right now. Spec doesn't properly install Klingo. So it just makes it a little bit easier. We remove our .spec directory. That just avoids a lot of the issues that you could potentially face if you're running spec builds in a CI/CD. But more importantly, we don't do, we try to put all of our spec configuration in spec.yaml, which is the single source of truth for, like, let's say when you're doing spec deployments, it's just one place where you have everything as opposed to different places to find spec configuration. And then this whole section in purple, this is more like just troubleshooting, but what we're doing is we're removing a directory, the root of E4S, and then git cloning the project, the spec project, with a specific branch. One thing to note is that there is an environment variable called spec_python that tells spec which Python wrapper to use for all of its spec commands. So we set this to the Python wrapper that we created from the virtual environment. And then, you create an environment, spec install, and this takes this takes the major amount of time during the install. And then we generate the modules, and then that's basically concludes our deployment. Now, just a brief note about how you generate modules from SPAC. We'll talk a little bit about this in the tutorial. So in the SPAC configuration, there's a modules keyword, and there is, let's say, you have to enable for each module system. So I think Tickle is enabled by default, but if you want to enable LMOD, you have to say LMOD. And then you have a property called LMOD, which is under default, that defines the LMOD generated SPAC modules. And then the same thing with Tickle. The one thing that's different about Tickle and LMOD and the way how SPAC generates them is that Tickle modules are the flat hierarchy. So this is the screenshot of the Tickle modules. So flat hierarchy means there's only one directory where all the modules are. And the way the modules are, the module scheme is set up, it's the name, version, compiler, version. And this is defined by the naming scheme right here in the middle. We don't use any hashes, so hash length 0 means that it doesn't put any, the SPAC hashes into the module file. And, you can set a list of modules to exclude with a blacklist. So in this E4S deployment of 2111, we had GCC NVHPC Cray MPitch that were SPAC packages that were explicitly installed, but we removed them. Now for the LMOD hierarchy, it's the one at the bottom right here. And it's significantly different. So we tried this out just to see how it works. The way it works is you have to module load one of the compilers, and then it exposes 2 other trees. This is only built with GCC. And you see Cray MPitch. This Cray MPitch is gonna load the hierarchy at the top, which are software built with Cray MPitch. Now, if you switch to NVHPC, it's going to show you a different tree. So note that the module names are name/version. So there's no compiler version because the hierarchy does the switching over. The trick with getting this to work is that you need to install the SPAC packages that are your compilers as, SPAC install, let's say GCC. And the way we did it is like we use a different compiler. Let's say we use the system compiler GCC at 750. That's your core compilers to generate the compilers as SPAC packages that does the module generation, if that makes sense. And then we set, let's say, suffix for, let's say, all packages that are built with CUDA. You can have this CUDA suffix, as you can see. Okay, so going forward, this is kind of a pipeline for the, let's say, 2111. The thing you want to take away is that there's different ways you can run the pipeline. One way is that you press play. So that's a scheduled event. In the job, there is rules that define how a pipeline is run. So for those of you that may be a little familiar with GitLab, there is a variable called CI pipeline source that is an event that it's an event that is set based on your Git activity, whatever it could be, and it depending on the action. Let's say if it's a scheduled pipeline, the value will be scheduled. If you run it through the web interface, then the value will be web. And for this pipeline, you have this unique name, Perlmutter E4S 2111. We can alternatively run the pipeline on a push event if there's changes to the SPAC configuration, which is hard-coded path. So the idea is that we don't want to run every single pipeline, but we want to selectively run the pipeline based on its the event. And then the script is the entire section for this deployment. The production pipeline is set up like how I showed you. There's a pipeline _ deploy. And there is an approved job that just kind of stages the production deployment. The way it works is that we have, so the approved job can only run through the web interface, and it's a list of pipelines that are deployment pipelines to run. And the job, when it says when is manual, that means that the job will only run with a maintainer of the project that can approve the job before it runs the production. And the way we have our GitLab stages set up is that the production deployment or the deploy job runs only after approved. Okay, so on this slide talks a little bit about the deployment of the file structure. So the software is actually deployed on Global Commons Software Stack ECP. That's the root directory. And previously, what we did is we did all of our deployments in the root, like something like E4S, and then the version. So that was 2105. That was on Cori. Soon we found out that when we introduced Perlmutter, we had to have subdirectories. So now what we have is Perlmutter and Cori as subdirectories, and then we'll have E4S and the version. Within each deployment, you're going to see three directories: modules, software, and spec. Modules is the root of where the module files are. Spec is a clone of spec. And then the software is where all of these installed packages are. Okay. So this is just some tips for doing deployment, even if you guys are doing it for your user facing stack. One of the things is that on NERSC, we have GPFS. So it's shared between Core and Perlmutter. So it's a good idea if you're doing deployment on a shared file system that you have something like, let's say, GPFS, some system like Perlmutter and Cori as subdirectories to distinguish between Cori and Perlmutter. If you're gonna generate, let's say, your own stack, consider having some kind of meta module or something like that that exposes module path, and that way you can use it to module load your stack. If you're going to generate modules via SPAC, consider using blacklist implicit equals true. What this does is it avoids generating modules for any dependencies. You can avoid hashes in module files. It kind of helps a lot because it makes the module load a lot cleaner. If you're going to deploy the stack, that's going to be, let's say, shared with everyone or even within your group, please check your UMask. If you do 002, it's going to help. I think by default is 007, but you have to check what it is. I'm going to briefly just talk about this, but we also have a support timeline for each of our stacks, where it outlines the release date and the end of support. When it reaches the end of support, we will remove the documentation, the files from the file system, any SPAC generated modules. We also send email to everyone, and then also remove any tests pertaining to each stack. This is our user documentation, so I think that's we'll talk about this in the next talk. Okay, I think I'm up.
So I think we have the Ryan next, if you're ready to go.
All right, hey everyone. All right, let me share my screen here. And how are we doing on time? Should I try to cut it a little bit shorter to get kind of back in there?
If you cut off 5 minutes, I can make up the rest.
Okay, sounds good. It's a deal. Of course, I say that. Who knows if I can cut off 5 minutes? We'll see. Well, I'll give it a shot. All right, so let me share my screen.
You don't have to worry too much. I think we also have 1 hour lunch break, so
Okay,
it exceeds a little bit. We can still
sounds
see.
good. Okay. Let me know when y'all can see this and I can make it full screen.
I can see it. Yes.
All right, perfect. All right, presentation mode. All right,
Looks
so
good.
hey, I'm Ryan Adamson. Until recently, as Katie had mentioned, I was the lead for software deployment at facilities. And it's nice there's a Ryan to Ryan transition. So if you have the name Ryan in your head right now for this role, you still use Ryan in the future. So that's great. What's nice is I think Mike and Katie did a great job. I mean, and Shazeb and Samir as well, just introducing sort of the software deployment pieces, like what we're doing with ECP to get the scientific software stacks to facilities. And I don't need to spend a whole lot of time, I don't think, explaining what E4S is, what SPAC is, that kind of thing. Just to say though that research software engineering is in some sense at odds with production software, right? Like when you write software to run in a production environment, you have lots of code review and planning and things like that. But it's not to say software teams don't have that in the research setting, but a lot of the times what you're building is actually a prototype, and or maybe it's not proven to work. And you don't want to load a lot of testing and hardening onto this research software until you know that it's going to work. And so I think with SPAC and E4S and the ecosystem of testing that we've built, we actually can do both now, and that's kind of cool. So as Katie had explained earlier, she leads the hardware integration piece, and the software deployment of facilities box, if you will, is tasked with taking the libraries and data and viz tools and programming models and runtimes and things and getting them onto the facility systems, which if you're used to like working on a university cluster or a smaller kind of commodity cluster that doesn't really have a lot of vendor specific pieces, I think E4S and SPAC installations and the containerization in that space works pretty well. The problem is when you have like serial number 0 systems, things that have never really been deployed before, along with custom vendor libraries, interconnects, drivers, and NPI, things under the hood. The facilities folks actually take software stacks and slap on top or lift it up above whatever the vendors are providing. And so there's this integration piece that is actually really hard at this scale. So as Katie had mentioned, the software deployment area has really 4 activities. The 2 we'll talk about today really are the software integration component of that, which is led by Shazeb. And then there's a continuous integration piece as well, which, as Katie said, is really about automating the things that we have like under the hood at the different facilities. And that's led by Paul Bryant. I like the phrase that Mike was using earlier. This is a leave behind slide. I think you all have probably seen this before today as well. But our job is to take these libraries and these tools here, pay attention to them, understand what they are, and then take the 70 of these things, right, and get them to the facilities. And as Katie had mentioned, you were sort of scratching our heads 3 or 4 years ago, like how are we going to deal with the complexity of all of these tools, right, which all came from probably a different background, different sets of developers, maybe some in the same spaces, right, different repositories, different tooling, different languages, right, and get them to something that can be useful for ECP. And so our first cut at this really was sometimes like a federated continuous integration model where maybe there's one GitLab server and then runners for GitLab runners run at each of the facilities. And we set up pipelines for each of these tools to automatically build and test as new versions of these pieces of software get pushed up to that. And we explored that and just realized there's a lot of complexity because you have 70 products, 3, 4, 5, 6 facilities with runners, and the dimensionality just explodes, right? And so but we ended up realizing that hey, this tool SPAC exists and the facilities have some experience with it. And Samir and his team have been working really hard on packaging up the software stack inside of E4S containers, and we said, gosh, is there a way that we could take the manifests that are coming out of E4S, understand how they're tested and what the guarantees are, and then take that and be that last mile to deploy them on top of whatever the vendor is giving us at the facilities. And that became kind of like this model that we all understood to be pretty reasonable, and it stuck. So that was awesome. I don't talk too much about this slide. Katie had mentioned it, but I do like to think of software right as it's written, as it's like red hot, right? It's bleeding edge. That's really what these arrows are, where they're hot, right? And then software kind of cools off. And the first step is the spec development branch, where there are some tests that are run before things get pulled into specs development branch, but it is still pretty out there, right? Things might not be guaranteed to work. You're kind of on your own for using that. But over time, when spec has release branches, that's more stable. And by the time that Samir's team has taken software that's come through this pipeline, it's had spec tests run on it, and the test suite tests have been run at the facilities for an E4S release. It gives us at the facilities a very, very high confidence level that it's going to be much easier to manage. And so what you end up with is almost like the stack of the software ecosystem. It's almost like the OSI model, right? Where you have a narrow waist in the middle, which for the OSI model is the IP layer, right? You have applications on top and then hardware on the bottom. Really kind of have the same thing here, where we have lots of AD applications that need libraries and are working hand in hand with ST to define the needs that they have with the acceleration. ST, you have to get these libraries down to the systems and facilities, and the testing really happens at all layers, but it's this E4S spec spanning layer at the middle that really, I think, helps us reduce complexity, if you will. So if you think about this model, let me go back for a second. I like to think that there's developers release new versions of their software, they get put into spec. E4S helps us curate and test, right? And then this is GitLab, which is where the tests are running, but really you can think of this as at the facilities. So there's really three kind of levels to this, if you want to abstract that out a little bit. There are the developers, the software stack curation, and then the facilities roles. And each of these roles have different responsibilities, and which means they're going to have different reasons to do testing, right? And it turns out each of the types of tests that these roles need to do can also be automated. So there's lots of dimensionality, to the way that you can look at this problem space. And in general, right, software developers are they know what they're doing, right? They're working towards new features or fixing bugs and issues. And at the beginning of ECP, a lot of teams actually already had automated continuous integration tests, unit tests, full integration tests running somewhere else, like in the cloud or at a cluster at a university or something like that. And so now those teams can use continuous integration tooling at the facilities, which is really cool. We offer that to the development area. In the middle, we have the E4S software curation team. They're implementing the E4S test suite, right? And they'll actually have accounts, at each of our facilities, and will build E4S ahead of a version of E4S before the facilities staff will. And so that's, they have their own kind of integration set of tests to make sure things work together. And at the facilities side, the tests are very much operational in nature, right? We want to make sure that when programming environment gets updated, that the right answers don't change, right? And so those tests tend to be more system focused and less software focused, but there is sort of like a spectrum of tests there. And so I think Katie and maybe Shazeb had talked about this a little bit, that we had some issues. I mean, so first things first, the facilities can now build way more software way more quickly than I think they've ever been able to do before because of what we put together. But because of the nature of these really extreme scale systems and vendors providing, tunings and things, it's still not quite turnkey. It's not quite turnkey yet for these really weird systems. so I won't go into this too much, but one of the Perlmutter PE updates really showed us that, hey, it's the same E4S stack, but it took us 6 weeks to track down all of the changes in the modules that happened, or some libraries were split into 2, some merged, some had different names, and pathing was interesting. And what that means is, while we might have enough continuous integration testing, in the ecosystem itself, maybe we need to put this up in the vendor space too, so that vendors can run a build against NERSC's, spec.yaml, the software stack configuration, to see what would break, right? And then they can use that as a gating mechanism for a PE release. So at the end of the day, packages aren't easy to install. Facilities only have a certain amount of people to do this. They're going to prioritize the packages that are easier to install, that have the most value for their users. And so if before it might take 10 users speaking up to say, I'd like this new thing, before someone would look at it, maybe now only 2 users have to say we're interested before the facilities will, or maybe we just pre-install things because it installs and we know it's going to work. So that's really what's awesome from a facilities perspective about this software stack. So speaking of CI, one of the things we learned in the last couple of years is that there's actually maybe 3 different use cases for CI, and there's really a value per cycle trade-off when you're thinking about these really big scientific instruments, right, like Perlmutter. Things like regression testing or unit testing, or other types of tests that you generally would expect to be able to be done anywhere, probably should be done anywhere but a scientific instrument like Perlmutter, right? That's one of the things that we've been realizing here, is that the time there is expensive, but time on the cloud might not be, or a cluster somewhere else might not be as expensive. That being said, right, like you do want to test performance, you want to test correctness, you want to test things at scale. We just have to be very careful about the suite of tests that we want to run from the as software is being developed. What we do see is more usefulness, like the value per cycle trade-off is better at this ecosystem layer, right, where Samir's E4S team is integrating the software stack that they're getting from E4S with some of the vendor specifics. We find more bugs in that space, and then finally on the facility side, you have to run some of these tests on the systems themselves, on the supercomputers themselves, because you can't really do the same kind of thing out in the cloud or on your desktop or anywhere else. So being aware of the value per cycle trade-off of the CI tests that are being run is I think really useful. Like Mike says, this is a leave behind. We've looked into the different types of testing that have been spotted within the ECP software ecosystem, and different pieces maybe fit better in different components of a workflow. And then Katie had talked about this a little bit too, that the E4S facility support model has been deployed. It's in production. If I'm a facilities person, I say production. What's nice is I think of E4S in some senses like Red Hat, right? Where Red Hat is taking the Linux kernel, GNU utilities and tools and other open source things. They're packaging them up into RPMs. They are testing them and they're deploying them. They're providing value, right? And then customers can get support through them. And from a facility perspective, that's really valuable because we can lean on others through service contract to help troubleshoot when something is out there that we don't understand. And so this E4S facility support model, we call it L2 support in some sense. Like if you have a problem and you send a ticket to the NERSC's consult queue, it's triaged. If it's something like file system issues, or hey, my token, my authenticator isn't working anymore, I need to change my password, right? Those kinds of things can be handled easily. But when it's something where there's a wrong answer, or you're hitting weird like locking or seg faults at scale, it might not be a facility thing to fix. That's where in the before times, the facilities have to reach out to the product teams themselves and hopefully maybe get heard, right? But having kind of an umbrella organization with E4S to manage that discussion and understand what's being seen where, and helping everyone who's using E4S, not just DOE, but everyone prioritize the issues that are most impactful to the open research community, I think is really valuable. So, and I expect the support model to evolve as needs change, but I think it's important before ECP rolls off that we've demonstrated something like this is sustainable and supportable and is really valuable to facilities to continue funding the scientific software stack. So this is that slide that Katie showed. It's I think if you want to see the slides later, you might be able to get at them, but this is pretty self-explanatory. A user working with staff to resolve a problem. So, and I guess that's all I have for now. If there are any questions, I can't see chat or the Google Doc right now. So if there are questions, let me know.
At this point, I'm not seeing any questions so far.
Okay, awesome.
So we'll give it another minute or so. So if you have a question, please. Okay.
All right. Well, thank you.
All right. Sorry, the next one is me. I'm Eric Palmer, and I'm a software integration engineer at NERSC. Can you see and hear me okay?
Sure can,
Yes,
Eric.
we can.
Okay, great. I'm going to give you the condensed version and get us right back on track on time. So what I want to show you today is that we have user documentation for the E4S package deployment that we do at NERSC. So what I'm doing is I'm here at the NERSC documents website. That's docs.nersc.gov. And to find E4S, I come down here to applications. I click on E4S. And this brings me to sort of I would say the documentation homepage for E4S at NERSC. The things to mention is that these docs are meant to be user facing. So we kind of put to the forefront the things that we think that the users are going to want to use when they're using it. There's also information here for people developing packages. And so I'll point out a few things as we go here. First thing on our trip here is to point out the end of support dates are listed for each version that we support at NERSC here. The next thing to point out that's important here is if you are using the E4S package and you want help, this is the button to click that will send you to the place where you can create a ticket for the NERSC consultants to answer your questions. And that'll go to me or Shazeb or Justin Cook, who's also on the chat now. And we'll do our best to help you. When you get down here into these links, you really get into the gory details of what's going on behind the scenes, which may be helpful if you're trying to solve a problem. So if you're just trying to get started off using the E4S stack at NERSC, I would suggest starting with 22.05 here on Perlmutter and clicking here, because this is kind of where things get started for you as a user. You are going to be in your terminal. You're going to type this module load E4S /2205. That's going to bring up the SPAC environment. We have a E4S environment, which is what you see down here, which will load our deployment stack of E4S. And in the interest of time, these are the configuration files. This is SPAC.yaml. You can click here to kind of go through the details to that if you ever need to. This is the list of packages that are available to be loaded with our SPAC E4S environment. And the thing that I want to point you to as just trying to get started, you want to load one of the E4S software packages so that you can build your software off of it or something like that. I want to bring your attention to this use case example. So in this use case example, we really just sort of walk through the steps of, let's say, suppose I have my own custom software package. It requires HDF5. I want to use the E4S package version at NERSC to build my custom software off of that. So I'll be, so that's what I'm looking to do in this use case example. So again, to keep things rather brief, I won't say too much more about this, except that this is the documentation that explains this, and this is where to find it. And I hope you find it very helpful. One other thing I want to point out here is, after just the basic loading of the package, sometimes, if you're developing software, you get into sort of some of the more detailed stuff, and that's what follows right after this, loading this package, explaining a little bit more about how to dig into what's going on what's happening in the environment. This is a nifty little trick that makes it easy to set the location of where the install prefix is. And these things are things that I found helpful in the past. And so we're passing them on to users in our documentation to make your life easier. So here there's more about, just using sort of the E4S packages through our deployment of the software. The next thing I want to point out here is we also have documentation sort of aimed at developers. So if you are developing a package like your own sort of SPAC package that you are wanting to sort of like exist in the E4S 22.5 sort of I would say environment, then this is sort of where the documentation picks up for you. And then last, we have this SPAC GitLab pipeline. This has some example projects of using, GitLab to automate sort of the building of the packages, but also to include our E4S deployment in that automation. And so you can see here for the SPAC nightly build and the SPAC CI pipeline, you have two example projects of that should get you started in that direction if you're looking to go that way. So I think that's a pretty quick, fast introduction of the user docs, but what I wanted you to know is that they exist, and you can find them by going to docs.nersc.gov, applications, E4S. It will all be here to help you. And if you need to discuss, talk to us, always the link here, help.nersc.gov, and we'll be happy to help you. With that, I'm going to kind of stop here. And I think the next thing on our schedule is a break for lunch until 12:30, but I'll let Shazeb kind of take us out.
Yeah, great job, Bert.
Thank you.
Yeah, so let's resume back in 1 hour. If any of you that need help with account access, please let us know. So the next session is going to be the SPAC training. So we'll be doing this on Perlmutter. So again, if you have any issues, just please let us know so that we can resolve them before the start of the session. And then I guess we'll meet again in 1 hour. Enjoy your lunch. See you soon. Okay. Okay, just have a quick sound check. Can everyone hear me and see my screen?
Yeah, we can hear you.
Okay. So I guess we can get started. So for this tutorial, what we'll do is we're going to do a SPAC training on Perlmutter. And I'm not sure, everyone's experience with SPAC. If you're completely new to SPAC, I just defer you to the user documentation of SPAC. And they have a pretty extensive tutorial that you can do. So for this tutorial, what we'll do is in the NERSC SPAC infrastructure, there is the documentation for the SPAC training. I've also put it in the Slack if you haven't seen the link. Maybe I should also put it in here in the Zoom chat. So, okay. So the first thing you want to do is actually be on Perlmutter. So once you log in first, let me see if I'm in. So, okay. Yeah, so if you need help getting logged into Perlmutter, I mean, it's just, there's a link right here that will tell you how to log in. I mean, you need SSH and you need to know your username and password. So in this tutorial, what we will talk about is how you can best use SPAC to install packages on Perlmutter. We'll give a little overview of the user environment and how you define compilers in SPAC, define package preference, how you can create a source mirror, how you build packages with CUDA, and generating module files. Okay. So the first thing that you need to do is clone this repo in your home directory, preferably. So let's do that. So this is the SPAC infrastructure project that's on GitHub. Okay. So the first thing I want to talk about before we get into SPAC is that SPAC builds are sensitive to your user environment. And any configuration that's set up in your startup shell can impact your SPAC builds. So some of the things that you should be looking out for is loading and unloading of modules. If you have any Python or Conda environments set up in your startup, things like $path that you may have set up, even SPAC setting that you may have at startup. I want to bring to your attention an issue that I raised up a long time ago that is relevant. So if you do module purge or unload any of like some of the Cray stuff, you're gonna run into some weird issues, and I think this will kind of help you kind of understand what kind of problems you will have. The first thing is that I have a really simple, let's say, SPAC configuration where I define a compiler and there's no specs installed. And then we're gonna have the list, module list is nothing. So what we do is I just purge the environment on Perlmutter. And if you do SPAC install, note that SPAC is gonna fail and it's saying that GCC has executables that are missing. We've defined the compiler definition with these modules and this order of modules. I mean, at the time of when I created this issue, these modules existed. However, when I restore back to our original environment, a lot of, and then just do SPAC install again, it worked. So there isn't a, like, I think there isn't, a response from the SPAC team yet on how to go about this, but this is just to illustrate that things can go wrong depending on how you have your startup modules, and anything like that. And we'll try to remedy this problem in some way. And I'll go back over here. So the first thing that we want to do, let me go back here, is if you navigate to the SPAC infrastructure project, oops. You should see a setup environment.sh script. So you just need to source this script. And what it will do is it will set up Python environment with Klingo installed. Okay. If you're using CSH, you will want to source the, we don't have a CSH script yet. Okay, so you have to be using bash for this. So yeah, we've installed Klingo and we have a virtual environment. So I wanted to also bring up another issue is that we've set this up intentionally so that SPAC doesn't fall over just by bootstrapping Klingo, which is now required with some of the more recent versions. And we have an issue for this. Typically what you would see is, yeah, if you try to just run any SPAC commands, you're going to get an error with SPAC not being able to bootstrap Klingo, and it just fails. So what we've done is we've just basically just let Klingo be installed in the virtual environment, and SPAC just picks it up. So yeah, I think this issue has been resolved, but I'm not sure if at the current state if it still works. But either way, it should still work if you just do pip install Klingo. Okay, so the next thing what we need to do is acquire SPAC. And in particular, what we'd like you to do is copy this command. So we're going to clone a specific version of a specific branch of SPAC. And this is going to take a little bit of time. And then once you have it cloned, you want to source the SPAC setup environment.sh script. So that what it does, it sets up the SPAC command in your shell. So that you can use SPAC. Okay. If anyone's having issues, please speak up or type your question in the chat. Hopefully after this, you should be able to run SPAC version and we should see these output. Okay. Now, one thing that we've done is the setup environment script has also set up the SPAC Python path to the Python wrapper. So if you do SPAC Python, this is the Python wrapper. This is the same Python wrapper that should be if you do which SPAC. And this is helpful in the sense of getting as clean of an environment as you can, as opposed to just relying on whatever the system Python is, which could change over time, or or you have something in your user environment that has its own version of Python or something. What were the two GitHub URLs? Yeah, okay, one of them is 27124, and the other one is this one. Okay. So SPAC Python path will show you the actual Python wrapper that's being used. And this is kind of helpful to make sure that you're using a Python wrapper that you use that is the one that is from the virtual environment. Okay. So one thing that I want to mention is when you're using SPAC, you may be tempted to just clone SPAC and then just start doing SPAC installs and package. One thing I want to mention is that SPAC is not, SPAC is a package manager, but it's not like you know, like pip or brew or something like that, where everything will just work automatically. You know, it's going to build from source almost most of the time, and then there's going to be errors. Think of SPAC as a tool to install software, but you need to manage your SPAC stack, like how you would manage your Python environments or Conda environments. So that way you can have your own software stack in a SPAC environment, and then you can switch to another environment or another SPAC environment. So hence, we're going to talk about SPAC environments. So if you're new to SPAC, you know, first thing that would help is SPAC is a pretty extensive command line interface with many subcommands. So if you do SPAC --help, you'll see all of the options. And then, you know, you can go into each of the subcommands and then do a help. And it's pretty helpful. If you need to find a particular option, you can just do that. So, and then also tab completion also works. So let's say you want to go into the SPAC environment. This is managing your virtual environments. And then there is create, which creates a new virtual environment or new SPAC environment. So what we'll do for this exercise is create an environment called data viz. And what SPAC will do is it'll create an environment by this name, and it will show you the path where this environment is stored. It's going to be a local, it's going to be local to the SPAC repo, and it will tell you how you can activate this environment. This is synonymous to doing like, you know, conda activate, or if you're familiar with the Python virtual environment, or you know, source activate the virtual environment. So what we'll do is run this, and we are now in the environment. So unlike, let's say, I mean, so similar to like Python and Conda, what happens is when you're inside the virtual environment, you're in your own isolated, let's say, environment where you can install packages and switch between to another environment and then install packages in there. So this would be helpful if you're like trying to do multiple deployments and you want to isolate them. You can use SPAC environment status. That will show you the environment that you're in. So that is helpful whenever you're using SPAC environments, especially when you have multiple environments. You can do SPAC environment list. That will show you all the available environments, and it would be. And if you need to activate, you can always specify the name. Okay, so upon creating this environment, there will be, if you want to know where the SPAC configuration is, there's a useful command called SPAC CD. Maybe I should do help. So SPAC CD, what it does, it can switch to different directories. It's basically equivalent to CD. But the -E will show you, it expects the environment name, and it will give you to the name, or it will navigate to the directory where the environment is. So this is a useful command that I do to switch between directories, and now you can see I'm in this really long directory path. And inside this directory, there will be a SPAC diagram. Hopefully, so far, you should be able to get up to this step. All right. So the next thing that we'll do is, I guess I'll pause. Does anyone have any questions, or are we able to get this far? Yeah, I don't hear any questions. I hope everything is going well. let's get started. So so the next thing that we'll do is we're going to define compilers. So on Perlmutter, you should see GCC and Cray compilers. So let's so if you run this, hopefully you will get access to all the compilers. So you see there's Cray 1302 and 1102. And what we'll do next is actually define these compilers in the spec configuration. Okay, so we're going to, you have to know what the modules are on the system in order to define the compilers, so that spec picks it up the way it's supposed to. So you use your preferred editor, whatever you like. And what we're going to do is we're going to define, you can copy this section of the spec configuration, and we'll just briefly talk a little bit about what this is. Let me enable. Okay, so the spec configuration is set up in a way where it's a YAML syntax. The top level spec is the is how you start the spec configuration, and each of the keys within the spec corresponds to different let's say configuration scopes. So the config just says some basic stuff about the concretization, where it's going to build, the concretizer, so that's Klingo. On line 13, that's where the compilers are defined with a list of compilers. You define this compiler as a spec, and then the key takeaway is that you have to define the wrappers and then the modules. So the way we've defined the modules is that, and they have to be in order of how they are loaded. So prog-m GNU, and then the GCC, and then this Cray PE and lit fabrics are modules that you should also load in order to build optimally for Perlmutter. Similarly, the Cray compiler is 1302. I know this because there is a module file 1302, and there's a Cray wrapper. You can probably even check the version, but it should correspond to that version. And that should be it for the compiler section. Now the specs, that's the list of packages that you want to install. And the packages is the section where you define your package preference. Inside here, what we're saying is that the compiler preference, so the compiler is a key, it's a list which is in order, and it tells which is the compiler preference to use. So our preference is going to be GCC followed by CCE. Okay. So I'm going to save this. So one thing to note is that the directory opt Cray PE default, this is this is a symlink that Cray provides to the default Cray PE, right? And if you do, let's say, which CC, you're going to see this. Obviously, this is the directory. Cray is going to change this over time, and as we upgrade our programming environment, this version get updated. So that being said, and then obviously if you do, let's say, MLT list Cray PE, you're going to see this corresponding module file right here. This is the module that's available on our system. So if you define, your Cray wrappers with this default, like right here, then you're going to get whatever the default is. If you want to be specific, you can change the default to the version. This is just something that you should be aware of as you're defining your SPAC configuration. As the system changes, you should also update your compiler preferences accordingly. So the next thing that we'll do is run SPAC compiler list. That will show you the compilers that are registered. And what we will see is SPAC's going to read our configuration, and it will show you that there's two compilers that we just previously defined, which is the Cray and GCC compiler. Okay, so the next thing that we'll talk about is package preference. Well, what we'll do is we'll just run this. So you can use SPAC spec, which will try to show you a concretized output of any arbitrary package. And I'll let that run. But the thing I want you to take away from this is that SPAC is going to do some interesting things like, well, I mean, so one thing that you have to note is that SPAC is going to try to install the package with all of the dependencies. And what I want you to take away is the stuff that's in yellow. A lot of things that are on the system has been previously installed as part of system packages, like OpenSSL, bzip, diffutils, readline, OpenMPI. We have CrayMPitch, we have OpenSSL, PMIX, whatever. And this is a good segue into one thing that we're trying to document is a list of SPAC externals that it's in this project. It kind of gives you an idea of kind of like a recommendation when you're using SPAC on what things to set as externals. And some of it may not be apparent to you in the beginning because there's so many SPAC packages. Like, Bash should be an external because Bash is always provided, but you never know if SPAC picks it up as a dependency. Like bzip, CPIO, that's provided, CrayLibsci, CrayMPitch. Things like CUDA, this may be a little unclear, but CUDA is available as part of the NVIDIA HPC SDK. So we have like the CUDA inside this. I'll talk a little bit about it when we get to that section. Things like core utils, that provides cat, ls, echo, and like all those commands. You don't want SPAC to install it. Things like diff utils or find utils that provide diff and find. So take a look at this when you're doing your SPAC builds. And if you need recommendations for externals, this would be the place. And we'll try to keep this as up to date as we can. Okay. So in order to define packages as what's called external packages, we're going to declare the package preference. And the way this package preference is set up is under packages, you can have the name of each SPAC package, which is a key within packages, and then you can have configuration for each of them. For instance, you want to say bzip2 is only going to install for this version, and the external means that look under /user. Okay. And then we have the same thing for all the other ones. So like typically what I do is I go and like look at the binary, let's say bzip2, and you see the bzip2 is this version, so I can tell that bzip2 should be at this version. It says it right here. This is 106. And then you kind of have to do it for all of the packages that you want to set as an external. So what we'll do is I'll copy this. And let's go into our SPAC configuration. And I'll add this. So a few other things to take away is that when you're doing any SPAC builds, there are some that you should definitely do. Not everything is required as you're doing builds, because this is obviously dependent on how you want SPAC to build. But you don't want SPAC to build things like OpenSSL, OpenSSH. These are things that you should just always let SPAC do. A few other ones that usually come to mind, going over here, you don't want SPAC to build Slurm. You're gonna you may not notice it yet, but when you're doing some really big builds, take a close look at when you're building, let's say, a package that's, I don't know, you're using a dependency like OpenMPI with this Slurm, or mpitch is Slurm, or mvapitch is Slurm. Because the problem is you're letting SPAC try to build something, and then if you get Slurm installed as part of SPAC, it's most likely not going to work. We already have a Slurm installed, right? And then things also like Bash, TCSH, and ZSH. You don't want SPAC to install other shells, which would rarely never get used. So just be mindful of that. Okay, so moving on. So other things that that you should be familiar with is the packages depend on stuff like MPI, BLAS, even PMI, libfabrics, and these are available on Perlmutter. So the MPI is cray mpitch, the BLAS is cray libsci, the PMI is cray PMI, and then libfabrics is the module that we have. So if you run this command, you should see all the defaults that we have: the cray mpitch, cray PMI. Yeah. So in SPAC, there is something called SPAC providers that tells you, well, it lists all the providers which correspond to SPAC packages that maps to a, let's say, a virtual package. So SPAC providers is also, you can say that it's the same as saying virtual package, where it's providing a similar functionality. Like for instance, MPI is a provider because there's many MPI providers. Same thing with like MKL or other things. So you can do like, let's say, SPAC providers MPI, and then it will tell you all the MPI providers. Like we have cray mpitch, cray mvapitch 2, NBHPC, OpenMPI, and all of that stuff. Okay. Sorry, I went a little bit ahead. Where to go? Okay. So the next thing what we'll do is we're going to update our SPAC configuration with the providers. So what this does is it tells SPAC to put the provider for BLAS to be cray libsci, for MPI to be cray mpitch, and we're going to define these as package preference with the externals corresponding to the module file that it belongs to. For cray mpitch, the way I kind of look at this is you have to know the path to the module file. So let's say we have cray mpitch right here. You have to do, let's say, let me move it over here so you can see it. What is it called? 8.1.15. you have to, if you do module show, and then at the bottom, you should see like kind of like the directory where Cray MPitch is installed, like right here. And that kind of tells you like where the prefix should be for the software like Cray MPitch and other things. Okay. So if that wasn't clear, like, you know, this is how I figure out where the prefix is. So for instance, the Cray MPitch directory, if you're doing the build, there is under OFI, so the Cray MPitch comes with different, let's say, builds with GCC, with Cray, NVIDIA. So if you're doing Cray MPitch external, we define a spec for Cray MPitch with GCC, Cray MPitch with CCE. That makes sense. And you'll see how this actually plays in when you're doing the spec build, when we install packages. So let's actually go in, update our spec configuration. So hopefully, if you just copy paste, it should just work. Save this. And now let's actually try to do spec hyper. So this is just another, it's just a simple product. Is actually part of E4S. And what we should see is spec is going to concretize, and it should pick up Cray LibSci and Cray MPitch as externals. So there you go, as you can see. So this is what you should get. And as you're building a big software stack, you should take a real close attention into the dependencies to ensure that you're building the package the way you want it to. If you see something that doesn't look right, most likely you need to investigate into what it is doing. And if you can set it as an external, do it. But what I would advise is, if you're unsure about whether the package should be an external, don't do it, because you may run into other problems in the future. Letting spec build most packages from source usually solves most of the spec builds. However, you don't want to let spec build everything. And that's why we have that recommendation guide on what things to do as external. Okay, so next what we're going to do is actually install some software. And the way you do this is you define the specs with the packages that you want. And what we're going to do is we're going to install basically Happy with both compilers, Hyper and Darshan runtime. So let's open up our spec configuration. Okay, so I will go here. I'll put this in. Okay, and then the next thing that we will do is concretize. So what concretize does is it's going to take your spec environment. Actually, before I do that, spec concretize, what it does is it's going to create a lock file. It's not created right now, but it will create a lock file that's a concretized, let's say, spec, and it will use that to basically figure out how to install all the packages. And the lock file is something that you never update. This is something that spec will auto-generate. The one that you will update is the spec.yaml. You can look at the concretized lock, the spec.lock to see what's going on. Think of spec.lock as synonymous to, if you're familiar with like pip file.log. So yeah, it's kind of like that. Okay, so this is concretize, and then the next thing that we'll do is spec install. You can see each of the specs and its dependencies, and we just do spec install. So this will take probably about maybe 5 minutes at most. We're hoping that this example will kind of demonstrate how this works. So I will take this time for questions. If you guys have any, please feel free to unmute yourself.
I just had an error and I don't know what that means. When I typed spec concretize, I could put it in chat.
Yeah. You have an error on line 50 and line 5. So maybe if you want to copy from the documentation, it looks like there's some indentation issue.
Do you think I should just erase it in?
Yeah.
Okay, I can try that. Thanks.
Yeah, this is just a YAML issue. It's not as, I mean, spec is just telling that. Yeah. I think we're done. Are we done with the spec? Any other questions?
Sorry, could you repeat what is the spec concretize doing? So it's creating that log file. What is it used for?
That's what's used for when you do the spec install. The concretize. So one thing to note is that spec concretize is something that you only use when you are using spec environments. So spec environment, you know, in the beginning when we showed you all the way here, right here, spec environment create, that's when you use the spec concretize. You're not required to use it. You could just go and just do git clone spec and just do spec install, and you know, it's not going to do anything. I mean, you don't need to do concretize. So yeah, once this actually finishes, I'll show you what the spec.lock is. But where is it? Yeah, so each of the specs that you specified in the spec.yaml, it will concretize and will show you all the dependencies that get installed, and it'll figure out its unique hash. And that's what's actually being installed. If that makes sense. It's the actual source of truth. It's the provenance of the entire, let's say, stack. If that makes sense. Did I answer your question? Or?
Yes, more or less, because I think is that something that we are still supposed to use, in the sense that I think that I saw in the Slack SPAC channel that they are going with a different way of proceeding, or maybe when you do concretize, there are different options.
Yeah.
But I don't. I'm new, so so I don't know if.
Sure. Yeah, so let me show you. So I think the spec actually did install. You got all of this stuff. If you do ls, there is the spec.lock, and this lock file is, you can use a lock file to actually install like if you want to reproduce the entire stack that you have built, and maybe you could like give the lock file to another user, they can actually get the exact, let's say, environment that you have. This is similar to like if you were going to share your like Conda environment or something like that. You know, you can give them the lock file and they can reproduce it exactly the same version. or similar to like requirements.txt, whatever. You can pin it to the version. The spec.yaml is the thing that you change and you make all of your changes there. It's not reproducible. It can change over time, but the spec.lock is reproducible. Okay. And if you are going to look at the lock file, I mean, it's quite long. It's good for troubleshooting, but this is something that you never update. Spac concretize or even Spac install will update this file. Just one tip: if you're doing Spac concretize, I recommend that if you want to regenerate the concretize or spec.lock, the -f is really helpful. Same thing with -u. If you're trying to do one-off builds and you have like some of the software built, this -U helps to build a new configuration, not using the ones that are dependencies. Or alternatively, you can just remove the spec.lock and just let Spac concretize again. Yeah, which is something that you periodically would need to do. Okay, so I think we have like 15 minutes. I want to hopefully get finished with this tutorial. So if you go in and you do Spac find, it will show you all the packages that got installed. As you can see here, there were 12 packages, including the Darshan Hyper Pappy. So the next thing we want to talk about is when you install packages from Spac, it will pull it all the tarballs from the web. And depending on the network speed, it can be time consuming. So it's a good idea to have the tarballs on the file system somewhere. Just one place that's just shared across all Spac instances. You could just, or even a group if you have a group share. So what we'll do is we'll do Spac mirror create, and Spac mirror actually creates an environment. And if you take a look at the -d, I can find it. Yeah, directory to which to create a mirror. And then -a is for mirror all versions. So we'll just run this, and what it will do is add all the packages that were installed. Well, I mean, all the stuff that was in your spec.yaml into this mirror. And these are tarballs actually. So let's actually navigate to this directory. So the mirror is actually in the root of the, let me see if I can do it. And you're going to notice that each of these packages have a tarball. Like, so the way it's set up is there's one per directory. There's hyper, pappy, and then you're going to see the pappy tarball, which is a symlink zlib. So with this, what you can do is you can just do Spac mirror, create, get all the tarballs, and then do Spac install, and then it will install from the tarballs. And that's much faster than having every single Spac package be installed from source. The other thing is that if you've done many deployments, this tarball is going to be useful over time, so you don't have all of these wasted space on the file system. You can just have one place. So the next thing we'll do is how to build CUDA packages. So on Perlmutter, we have CUDA toolkit. This is a standalone module file that provides CUDA. So you can see this if you do CUDA toolkit. There should be, there's 3 versions right now of CUDA toolkit. And we also have NVHPC, which is the NVHPC compiler. So we're going to define both of them. And again, the ones that I think that right now we're using are these ones, not these ones. Okay, the NVHPC. So the way you would typically look at the NVHPC is that, you know, you could do module show and look at the directory. I know that the directory is this. This is the root of the NVHPC directory. And what we're trying to do is figure out where stuff is actually installed so that we can define the package preference. So this is the root of NVHPC. You're going to see compilers, CUDA, examples, math libs, which are all useful stuff. The CUDA stuff is actually inside this under CUDA. And you're going to see 11.5. And then obviously the bin points to the bin. So if you just go like this, you're going to see NVCC right here, right? And the CUDA runtime libraries are going to be, let's say, in the lib 64. You're going to see right here. Okay. So what we'll do is we'll also install PAPI with plus CUDA that enables CUDA support. And that's right here. So I'm going to take this, add this in. So I'm not doing anything special. I'm just adding another package. And I'm going to add in CUDA. So let's go into get build. I think this is right. Oops. Yeah, you want to make sure that all the indentations are done correctly. Yeah, so that's right. Yeah. Okay. And then we do SPAC installing. So what it will do is it will try to install PAPI. That's the one with CUDA, and hopefully this should just work. May take a little bit of time. Okay. Okay, so far, how is everyone doing?
Just I have another question eventually for the mirroring step. So if you are using a develop branch, is SPAC gonna check if there is something new in the mirror? Or because I understand that when you are downloading a particular version, then you can keep it there, it's not gonna change. But if you are working mainly with develop, who is checking that there is not something new, or how does it work? Do you have to maybe not do the mirror for that?
When you mean develop, you mean a develop of a, let's say, some package, like I would say.
Yeah, like for example, Cocos, they have the normal release numbers, and then you have the develop branch. In that case, you think
then you don't do that, because that could be a little confusing, because like, let's just say, because there's only one develop, right?
Yes.
It's called Cocos that develop, and if you do SPAC mirror create, you're pulling in the develop branch. I mean, the develop tarball of whatever Cocos is, and that could impact. So in that case, I don't think that's, for that workflow, you probably are better suited to not create those mirrors and just let SPAC just install it from the web, if that makes sense.
Yes, so in the mirror statement that you put, SPAC mirror create, is this gonna do mirror for everything that you, or can you specify only what you want?
Yeah, so you can do one-off specs. Let me get once I get the install, I'll show you, but the SPAC mirror create. right now I did -A. So you don't want to do -A. That will basically say, go and find every single spec that you have and just pull it into the mirror. There is a positional argument that is the spec. So you can say spec mirror create, let's say Coco's at version, and then it will only pick that spec and download it.
Okay, thank you. Yes, thank you so much.
Yeah, so if you create, you can see this right here. Let me go like this. Positional spec. So this is one or more spec, and then it would just work. Yeah, and then you don't want to use -A because that will just get everything. And then you can do some other things like this or this. I haven't really tried them, but okay. So we got CUDA, we got Pappy built with CUDA, so we should be, if we do spec find, you see this right here, Pappy with CUDA. There is 14 packages now installed. So the next thing we'll do is we're going to try to define NVCC or NVHPC as a compiler. Oh, sorry. Right now, what I want to show you is the NVCC binary from the CUDA, so that when you're defining a package, let's say preference, I probably missed a step. You want to make sure that the compiler version that you define, I mean, the actual version that's reported by the NVCC version is maps according to what the spec package is, right? So that's what we do right here. When we said CUDA is buildable false means don't install any other CUDA versions, pin the version to 11.5.0, and then define this as a spec. Okay. Now, if you don't know, there, you can do, let's say spec info, any spec package, and it will show you all the, let's say, versions along with the variants that are available. And this is a very useful command. So if you need to know, like, yeah, here is 11.5.0. So that's the version that you want to pin this CUDA package. Okay. Next thing we'll talk about is how you generate module files from spec. This is optional if you prefer using module load. This is possible. So on Perlmutter, we have LMOD. If you do module version, you would see, this is it's a Lua modules, and this is LMOD. It's developed by Robert McClay. In order to do for this tutorial, what we'll do is we'll generate only Tickle modules. And in this over here at the very bottom, what we're going to do is define the modules keyword. We're going to enable Tickle, and this is the Tickle, let's say, settings. You're going to blacklist implicits equals true means ignore module generation for dependencies. Hash length 0 means don't add any hashes to the module file. This is the naming scheme. And these variables, which you call, these are something that SPAC understands. What this is this is the name of the SPAC package, like HDF5. This is the version of that package, like HDF5 version. The compiler.name and compiler.version. This is the compiler used for that specific build. And then you can have settings for the all. This is for all modules. So you can say something like auto load direct. That means automatically load all dependencies. And you can set like environment variables. So this is saying set something like name _ root to the prefix. You can set, let's say, all CUDA dependencies have the CUDA suffix. The suffix are key value pair, where you can use a spec syntax like this, where caret, the symbol is for dependency. So this is saying any packets that depend on CUDA, put the CUDA suffix in there. So let's just go in and copy this. And let's save this. And then the next thing that we'll do is we're going to create the module files. So the module files are created using stack module. In the stack module, there's Tickle that generates the Tickle modules, and then there's Almod. For Perlmutter, you can generate both of them. Under Tickle, there is what's called refresh, which would regenerate the modules. And something that I do when doing this regeneration is I always just remove the whole directory tree and then just let it build. And then you can just say -y, that's for confirmation. So what we're going to do is we're going to just run this command and take a look at the output. The thing that you want to take away from this is things that are being implicitly ignored. This is saying don't build module files for these stuff because zlib is a dependency, cray-mpitch is a dependency. But over here, you see right here, where it says darshan runtime, it's going to write a module file all the way here to this directory. And what you want to take away is this is the naming scheme. This is the actual module file. Does that make sense? Over here, you see this? This is another one. This is another one. So I use the debug, which is the -d, for troubleshooting the module generation. And then we're gonna just to show you what it looks like. This is done. The module files are actually generated right now in the root of the SPAC directory. And what you see is there is a module for darshan runtime, hyper, happy, all of this stuff. Okay. So right now, the thing that you notice is that it's generating within the SPAC project. But if you prefer to have it in a different place, like a central, like home directory or something like that, we can do that too. I'm just going to show you that the way to do this is something like this, where you say root, pickle, and then the location. And I'm not going to run this command, but I mean, you'll get the idea. If you run this and regenerate the modules, you can set it to something like this: home, SPAC infrastructure, modules, and then it will work. Then over here, you would see under the root of the directory, the modules, and then you can say module use. And now you see all the software that's built. So that concludes the SPAC training. I hope this was informative and you were able to complete it. And if you have any questions, please ask them now until we switch to Samir for the next session. Did anyone have any issues? Okay, I don't see anything. Samir, you can take it away. Good luck.
Even there one question. So do you have from your experience with the users, do they prefer the TCL or the LMOD representation on the systems?
Yeah, so we tried the Tickle. So we provide the Tickle modules. It's much easier than LMOD hierarchy. However, in our most recent deployment that we did, that's the 2205, we don't generate SPAC modules anymore. Part of the problem is that it's a little tricky, first of all, to get all the modules to work nicely with all the other externals, like not externals, but I mean other external module files, like things from Craype and other module files. But then the other problem is that users find stuff when they do module spider, and they see a lot of software, and then they start using it. So one thing that we thought about is don't generate modules and force users to just use SPAC load to find the software. Because SPAC load will allow all users to use any software that's in this that's built by SPAC, whereas the modules are only limited to the module files that we provide. So we don't provide every single module file. That makes sense. But Tickle is probably the thing that probably users are familiar with, given that they have worked on Cori. LMOD modules are going to be a little tricky with the hierarchy.
Thank you so much.
Yeah, I think you're on mute. Can't hear you.
Okay, can you hear me now?
Yes.
Okay, you can hear me, right? Okay, great. So we are monitoring the questions in the chat, and I'll be doing a hands-on session. So if you have access to Perlmutter and you can log in, that would be helpful. So we saw how E4S is installed on Perlmutter, but I'll go into some details. We are working through ParaTools for providing some recipes to the HI team, to Shazeb, for every new release for deployment and GitLab build test, CI testing. And here is an example of some of the packages that we have built using MVAP-H2 3.0a and Prog and GNU on Perlmutter. And the general idea here is that you can use a module use command like this, and then pick the module, or you can go to that directory and it has a spac.yaml and start spac.sh. So if you source that, you can also get the SPAC-based environment. If you say module use and do the module avail, that works as well. And typically it works like this. You can say module use, module avail, and then you can see these two 22.05 environments and load one of them. And in this case, MVAP-H2, it will give you MPI-CC for building. This has support for the Slingshot 11 network adapter and Slurm as well. And here is an example of module avail output on Perlmutter with the ParaTools installed version. It's in this directory, and you can see all the modules that are available. And these are the paths to the MVAP-H2 installed packages that you can see. There are about 74 packages that are installed using MVAP-H2. And if you use Prog and GNU, then you can do similarly a Prog and GNU environment load, and then look at the modules that are available. Now, I should mention that the better way to use Prog and GNU is not to use the ParaTools directory, but just the system installed directory that Shazeb was talking about. So if you just log into Perlmutter and you can just say module avail E4S, then you will see this E4S 22.05. This is the system installed. This is the NERSC installed version, which differs from the version that I showed you earlier, which the ParaTools team has installed. And so you can just say module load E4S, and it will load up this 22.05, or just explicitly do this, and it will give you the Prog-based version. And then you can just say which SPAC. You'll see this is the location of SPAC. SPAC find will show you all the specs that that NERSC has installed for E4S, and then you can pick one of these with SPAC load command, as we saw earlier. Now, what's also interesting is that you can also daisy chain the SPAC environments. I mean, you have one that comes from a particular location, and you may have another that you have just checked out. And so you can see, like over here, there is a whole web page on SPAC chaining. I'm just putting it in the chat window, where you can specify an upstream instance 1 and 2, which one could be your instance, the other could be an instance that comes from E4S installation from the system staff or paratools. And then you can use a combined set of packages, which may be better than just using one package that you've installed yourself. But this is the recommended version of the E4S, which is the E4S 22.05, which is system installed from the global common software NERSC. And you can load it like this. And if you want to see the version that we have installed from Paratool side, you can see all the packages and where they are located with the commands I showed earlier. And here's the 22.05 with the mvapage2. And here are the prog and GNU packages that you can see over here. There are 81 of these packages. These are core specs, and then of course there are some dependent specs that are also available. Now we also have container-based deployment of E4S on Perlmutter, and we are using Shifter for that. Shifter, as you may know, comes from Berkeley Lab, and if you want to see which images are there pre-configured and ready to use on Perlmutter, you can just say Shifter IMG images. Now the output is huge, so I'm restricting it by just saying grep E4S and grep the 22.05. And you can see that there is a CUDA version of E4S 22.05, and there is a base CUDA version. This is a much smaller container which has just CUDA, maybe CMake, MPI, and nothing else, not the full list of packages that I just showed you. And how do we launch it? You can say Shifter with the -- image equals this with the bin bash and give the -- rc file as etc bash rc. Now we are going to try this. We are going to try this in the hands-on session that we'll have after I finish with the slides. It's also important to note that Shifter has an environment propagation by default. And if you don't want the Cray environment to merge with the environment on the container, you can give a -E, an uppercase E, and then it will not do that. And then again, you can give a --env if you want one variable to be passed through, like display or so. So you can selectively choose what environment gets passed. By default, everything gets passed. And here is an example with Shifter image equals this, RC file is this, and this is the base image. Now, even with the base image, you can see that you're inside the image after you do the Shifter command. You can see the etc OS release says Ubuntu, not the / from Cray PE. And here I say NVIDIA SMI, and on the login node, I can see that there is a GPU with A100 with 40 GB of memory. And then SPAC find can just show you the bare bones, bare environment that's there, but it also has NVHPC 22.3. So if you wanted this version of NVHPC with CUDA, then you could use this. It also has a MPage installed in it and CMake, so that you can be productive and create your own images based on this. Now, if I say grep for the 22.05 and get the full featured image, then it has a lot more packages installed in it. And I can even say, show me the packages that were installed with the plus CUDA variant, where the CUDA architecture is 80, the SM80 flag, or the A100. So these are all the packages, including Cocos, built for the GPU. So we have Raja and Cocos and all of these packages. If I launch Python and just say import TensorFlow, I can see that it recognizes the GPUs, and there's a GPU available over here. So with this, let me just move on to the other interesting problem, which is I have MPI, I have all these packages in the container. and I build my application. Okay. Now this application is a binary that refers to libraries that are inside the shifter container. But I want to run it on the HPC system and replace the mpitch that is embedded in the application binary with the system MPI. So on the HPE Cray system, on Perlmutter, we have Cray mpitch. I want to use that Cray mpitch. So why would I want to do that? Because I can then use the native interconnect between the nodes, and they are already pre-configured to use the Slingshot 11. So I could have the application and data external to the E4S container, which is read-only, and then the programming models, compilers, runtime libraries, and tools are inside the container, and we can replace MPI using the mpitch ABI or the Y4 MPI compatibility layer that comes from CEA France. So the goal is that I should be able to build an MPI binary just once and run it unmodified on all the HPC Linux clusters. So for the same processor architecture, of course. So if I had a Linux laptop, I could download the E4S, I could build it in that environment in, say, Docker or Singularity, and then I could just transfer the binary to Perlmutter and run it there. Or I may build on Perlmutter itself and compile and run over there. And to do that, we have a tool which is called E4S CL. It's a tool to simplify the launch of MPI jobs in these containers. So how do we use it? There are just two main commands that you should remember. One is the E4S CL init command, where you can specify which backend to use. On Perlmutter, I'll use shifter. On some other machines, I could use Singularity or so. And then I point to the image. This is the same image that I see on the shifter IMG images output. And then I give a source command for startup commands like this. And then I can just do a module load on the Cray mpitch ABI, and then do the init like this and specify the source file. In the case of an example that uses, say, Trilinos library, I may use the spac load Trilinos command like this. And then I can just say srun -n and then the application. What this will do is it will figure out which libraries it needs so that you can have all the Cray mpitch libraries work with the libraries from the container. So here, Trilinos is coming from the container after loading up spac from this directory, and then I am able to run it with an unmodified binary like this. So this is the hands-on session that we will do. I have several examples, and what I've done is I've created a tarball, which you can get from this https e4s.io/tar e4stests.tgz. Then untar it, go to this test directory, look at the README file. There are README files in several directories. What I'll do is I will launch 2 nodes in an interactive partition, say maybe for an hour, and specify the constraint as GPU, 4 GPUs on that node, and give my account ID. My account number is M3896_G. You're probably likely to have an account that is different. Please replace this account ID with your account number. And then we will look at this example with the shifter, specifying this as the image. Maybe we can start with the -E so that we don't even import all the environment from the container, from the Cray side. And then we just have a fresh environment inside the container. Okay, and we'll run this example. We'll come out of the container so that we are back to the main slog environment, and then we can run this E4S CL command and look at the output. There are some other examples and tests as well. And this is the architecture of E4S CL, where we have the execute and then the library resolution with the MPI libraries and the host libraries. And then I would like to thank the Exascale Computing Project for their sponsorship of E4S. And let us go and do this hands-on session. So what did I do? Waiting for auto logout. I hope not. I did a SLOC over here like this. Let me put it in the chat window so everyone can see this. Please use your different account ID. Then you can use the example, the instructions over here, where I'll do the wget. Tar E4S tests.tgz. Okay, and then tar this E4S tests.tgz and go to the E4S tests directory. So everyone with me so far? You have this tarball. I hope you are able to download this. You should see a README file which specifies how to launch the commands over here. And then you can see some examples over here. We are going to look at the Zoltan example right now for the E4SCL replacement. But if I want to look at MPI proc name, it shows you how to compile the code. And then srun-n2 foo, it will run this example on 2 MPI ranks. And you can see that it got 2 separate MPI ranks. And here is the foo.c, where I'm just doing a print statement, hello world, I am rank this out of this running on this processor. So I just wanted to make sure a sanity check of sorts that when I did a SLOC -n -nodes 2 and I do a srun, I'm running the example on 2 separate nodes, 1061, 1064. Okay. So I'll take a minute for everyone to catch up. Please do the wget as I have shown on in the chat. And then we'll look at this README file in the Zoltan directory. Is everyone with me so far? First of all, is there anyone who is unable to log into Perlmutter? Can everyone download this tarball?
I'm able to log in, and I was also able to do the wget.
Wget, okay.
Yeah.
Are you able to do the SLOC to get 2 nodes?
Yeah.
Okay, good. So then you can go to the shifter, to the Zoltan directory, and run this shifter command like this. Okay. So if you would like to try this SLOC and then this MPI proc name, you can just quickly do a sanity check too, that when you do a CC and then srun, you're actually running this program on 2 separate nodes like this, 1061, 1064. So I want to make sure that we are able to use the network interconnect between the 2 nodes, the Slingshot 11, using the prog-env GNU. Okay. So here I will launch the shifter command in Zoltan. But let me just wait and check if there is anybody else who is not able to wget the tarball or are still waiting for the SLOC nodes. Please feel free to unmute yourself or type in. I see Richard is waiting for resources. Anybody else waiting for resources? It's always tricky when you're running on a production system.
I had a problem with running the script, the run E4S.
Okay, let's look at it. First of all, let me do a shifter like this. And I have launched shifter with this image. Now, in this case, you can see I have a script called clean.sh, which SPAC, I'm getting SPAC from within the container. Okay, I did a -E over here so that the host environment does not propagate. I'm using etc bash rc to boot it up. I'm inside the container. How do I know that? I can say etc os release, and it will show me Ubuntu. This will tell me with this bash base that it is using the E4S container using shifter. So in this Zoltan, I'm saying the Trilinos is located over here. Here is the location of the Trilinos. You can see it is coming from this directory. And I'm going to do a clean.sh. I think we don't need to, but let's be sure. Okay, then let us look at this README file and say compile.sh. So what did I do? After going here, I went to the Zoltan directory, I did a clean.sh, and then compile.sh. So this is built now. And if I say ls Zoltan, I have the Zoltan binary. Okay. If I did a MPI run over here and ran this like I do over here with run.sh, I could run it all within the container. It will work. I could say run.sh. So Richard, you can ignore that Darshan message. You can ignore that message, but at least I'm glad to hear that you are able to run. There's some Darshan issue where it's trying to create log files and there's some problem with it. You can do a module unload Darshan, which is a default loaded module. It's a tool that tracks the usage of the resources and tracks the IO usage in particular and creates log files so that it's enabled by default. So here is the run.sh. The program will still run properly. Okay. And here I'm running it on just 4 MPI ranks, all within the Singularity container, all within a single node, not going cross node, but just a single node. It's taking, about 4 seconds, the total time. And then I can come out of this container. So here I was with OS release, Ubuntu 20.04, I can exit and then again type OS release. And now I'm on SLES. So I'm outside of the container. This is very important for the E4S container launch tool to work. And let us try running this E4S CL.sh. I hope all the permissions are okay and there's no read problems. I have the container launch tool already installed in this installation directory, which I'm putting in my path. The executable name is called Zoltan. It's in the current directory. I'll make sure that it's there over here. But if I do an LDD, try to load it, you'll see it has all these libraries that it doesn't find. And why is that? Because these libraries are inside the shifter container with which it was built. Now I want to use those libraries, but all of those libraries are also using the mpitch that was inside the container. I'm interested in using the Cray mpitch, which I have loaded like this. And what I'll do is I'll say E4S CL init, and then I can specify the launcher as srun instead of MPI run, even specify the arguments like this. so that I could even launch it outside of the SLOct session. And there are these three example arguments. There is the shifter backend, there is the image of 2.20.2.04 and the startup scripts. And in fact, to get even faster performance, you can unpack the environment of the Trilino startup script. The Trilino script looks a little bit like this, where you just load up the SPAC and load Trilinos. So we will just run this script and try to run this on 2 nodes like this. And I say run E4SCL.sh. Now here it figures out which libraries it needs, how to do the manipulation, and then it creates a database, it stores that info, and there it ran that. Now, did you see this ran in 1.11 second? This is using the really fast inter-node connection on just two MPI ranks, but I'm able to run this example. So you should be able to create the Zoltan binary inside the container, and then you should be able to do the run E4SCL.sh. And there you will replace the MPI in the application with the system MPI and use the 2 nodes. Now, I'll wait now and see if you are able to do this. Just exit from the container. You can cat etc os release to make sure you're on the host. And after that, you just say /run E4SCL.sh. Can somebody confirm that they were able to launch Shifter with that image? They were able to go into the Zoltan directory. They were able to clean and compile that executable, come out of it, and do the run E4SCL.sh when you have
Yes.
2 nodes allocated?
Yes, I can
Yes.
do that.
Okay, good. So this is the example where we have got E4SCL working with OpenMPI, with CrayMPage, with MVAPage2. So then the container immediately becomes very useful because you can then compile with everything inside the container. And then you can run it on bare metal nodes without requiring a lot of manipulation of the command line. You can do this manually too. You can run this manually without E4SCL. But for every container runtime, whether it is Docker or Singularity or Shifter, you will need to figure out for that MPI which libraries I need to preload or put in my LD library path, which file system I should mount in the image and run it. And that can be cumbersome for the users. If you want to see an example of doing that, there is a run.job script which will work. Here is the example where I'm doing this. You'll of course need to change your account over here, but you have to export things like opt, UDI image, modules, mpage, and then you have to source that. Then you have to remove the SPAC, unload mpage, and do all that. If you don't use the run E4SCL, if you want to use it, you can just use it like that with the run E4SCL. And it will take care of all the management of these libraries for different APIs. And there it runs the application. Richard, are you waiting for the compile to finish or the run to?
I'm waiting to get nodes.
Oh, you're waiting to get nodes still. Okay.
Yeah, so I have no idea what you're doing. Because I'm like 5.
Okay. Can you see my screen?
Yeah.
You can see the screen, right? Okay, okay.
Yeah.
Just making sure that.
No, I can see your screen, but if I can't get the
Yes.
nodes, I can't do step one. I can't
That's
run
right.
.clean.sh, compile and run until I
So
get
here is the interesting
4
thing.
freaking nodes, right?
If you want
Sorry.
to do the compile and run it inside the container, okay, although that's not recommended, you can at least do the clean and compile even on the login node with this. You just do the shifter command on the login node. You should have GPU access, and then you should be able to do the clean and compile.sh even on the login node without the SLOC. Shazab, does that work for you without errors now?
I think I was able to get it
This
to work.
run E4S.cl.sh is working?
Yeah, my concern was that at first I was running E4SCL from inside the container, and then I realized I think I need to run it from outside the container.
Yes, of course, because
So
it
then
does not
I
even
exit-
exist inside.
Yeah, so then I try to run it. I think this probably is more of a ZSH issue, but for some reason I don't see the modules. It may be something that just works with Bash, because what's happening is when I run the command, maybe I'll put it in. So I'm putting everything in the Slack channel.
Okay, we will look at that. Is there somebody else who can confirm that this worked just as described in the README file here? I think Helen said it worked for her, right? Are there others on this Zoom session where you have been able to get the SLOC nodes like this? And you are able to run the shifter and Zoltan?
I have no idea why that is.
Can you share the command that you ran for the SLOC?
I used this SLOC command.
No,
I'm putting it in the chat window.
Richard.
Yeah. Richard, you use the _G after the account name, right? And you checked that you're in that same group with the groups command.
Yeah, I used them _G.
Okay.
I use my account number with _G, and I have an allocation for that.
Richard, I think you've hit a QoS limit. It looks like you've got 2 other jobs already running.
Yeah, I don't understand how that could be. I only have one window, and it's just an interact.
Something may have not exited properly. If you do SQS, you should be able to see them, and you might want to cancel one or both of them.
Okay, hold on a second.
Anyone else waiting for allocation of nodes or having trouble running this E4SCL tool on Perlmutter? Okay, let's look at some other things that are there in the container or even in this tests directory. I saw this MPI proc name. Let us go to Cocos CUDA. Okay, let's look at the README file. And this is a test that I will do on the host itself. Okay, now here, if I say which spec, I don't have any spec in my environment. I can just say module load E4S with 22.05. Okay, if I wanted to use Cocos on this, and I say module avail, say Trilinos, by default, I don't have any Trilinos installed. If I say module avail Cocos, I don't see any Cocos available. But if I say module load E4S 22.05, the module that was built by Shezeb's HI team, and I say module avail Cocos.
Yeah, so sorry, we recently
find
changed
Cocos.
it. Yeah, so we don't generate modules, but yeah, you can do spec find and then spec load.
Yeah, and
This
this
is a
is the
very
spec
recent change.
module. It has, I mean, we see Trilinos over here. I see Cocos over here. I could even say spec find Cocos plus CUDA. Okay, and it will show me the CUDA package over here, one installed package over here. So let us try clean.sh. And then I say compile.sh. Okay, here is compile.sh. And it will build this Cocos example. What is this example? It's a simple example that just tries to calculate the number of even numbers between 0 and n-1. You give the n. And it's building it with the Cocos that's installed on the system. I'm outside the container. There's just node level parallelism that I want to exploit. And here's an example without any Cocos, and there's an example with Cocos that it builds. What is this example? It's a foo.cpp. This is the example where you can see that it calculates sequentially the number of, I%2, the number of even integers between 0 to n-1 actually, and it just increments a count. But in parallel, it creates a parallel reduce operation with a functor, and this is the count functor, and it says the argument is n, help me count the number of even integers, and this is the count functor where it looks at the L count and increments it if it is I%2 is 0, and then it does a reduction operation, the parallel reduce. And here is the initialization of Cocos in main. Here is the std out, and then here is the finalize. If it's not, if the arguments are less than 2. So I have to give the n on the command line. And then it gets the number n, it creates this timer, it does this whole application. So I go to the build directory, and then I can say example with Cocos and give some large number, say, how about 10 million? Is that 10 million? And it shows you that it has found 4 GPUs, and the number of even integers from 0 to 10 million is 5 million. And it does this in parallel in just a fraction of the time it takes to do it on the CPU side. So we are doing the CPU here and the GPU over here. So what did I do to do this? I did a CD to the Cocos CUDA directory. And then I did a module load E4S 22.05. And then I did a clean.sh, compile.sh, like this, and then go to the build directory and say example with Cocos, and give a large number like 10 million. So now with E4S, if I wanted to use Cocos, I have an easy way to get access to all the Cocos libraries on bare metal Perlmutter without the Singularity container. If you wanted to use the Singularity container, if you wanted to use the shifter container, you could have used the same example with shifter as well. Now here is Python tests. If I wanted to use the Trilinos, if I wanted to use the TensorFlow and PyTorch from within the shifter environment, I could just do this shifter and then run this set of tests, which are going to use, if you get such messages, remember, you may have forgotten to put the -e. When you put the -e flag, it will not take in the host environment in the container. Okay. And there you get a clean entry into the container. And then you can see f1.py, f2.py. Here, this is using TensorFlow, PyTorch, and using the GPU. And if you see the run.sh, all it's doing is running all these tests, which I'll do now. Here's the first one, F1. This is F2. And then you'll see the TensorFlow, PyTorch, and other examples. So there are several examples. Here, PyTorch is using the A100 GPU. And again, in this case, the application and data are outside the container. The container just has pre-built versions of TensorFlow and PyTorch, where Python in your path has access to these AI/ML tools. Okay, does this work for everyone? Can you try this CD shifter and then go to CD Python tests and then just do a run.sh? Richard, you're still waiting for the nodes? And you can see TensorFlow can see 4 of these GPUs, and it's doing the model training.
No, I'm not waiting for the nodes. I'm just trying to catch up. I'm still back in Zoltan.
Oh, okay. I hope you can go in the container, look at the README file, just cut and paste it, and just do the exit from the container and the run E4S CL.sh.
Yeah, it's good to have instructions so you can do them asynchronously. Because if you run into any problem at all, you fall behind and then it just turns into a car crash. So
yes, that's why I have README files in every one of these directories, and I'm just doing the commands from the README file that you can just cut and paste. So I can see PyTorch on the CPU, PyTorch on the GPU. Here is TensorFlow working on the GPUs. And there are more examples like that. On the host side, you can do some Trilinos CUDA examples as well. And I also wanted to show you, whenever I get an allocation of 2 nodes, I typically I need to load the E4S 22.05 and then it's a SPAC load. Sorry, we should be using the system installed version. And you can look at the Zoltan example for that. I also use the OSU micro benchmarks to check, like if I see which CC I'm outside the container, I can just say /x, it will build it. And then I can check the latency, make -j, make install, and check the OSU micro benchmarks, like in the install directory, OSU micro benchmarks. Point to point, and say srun-n2 OSU latency, the latency between two nodes. I can see like 2.1 seconds, microseconds. And then I can say srun-n2 OSU bandwidth and see the bandwidth between the nodes. And that is nearly 24,000 megabytes per second, which is close to the limit of the, of the network interconnect. It's getting about 191 gigabits per second between the two nodes. So I can see the good bandwidth before proceeding with any of the other executions. And to do that, the other thing that may be a problem is the -e. You see, when I cut and paste from my from this window in Zoom or PowerPoint, sometimes the capital -e may have a weird character that gets inserted. You may want to remove the -e and put the dash again, Larry, and see if that helps. So instead of some weird cut and paste character, I just use the type in the dash.
So Samira, we have like about 10 minutes or so.
Okay, so
I guess you could,
I'll,
if there's anything else you want to do before we go into Q&A.
I think with this, we'll stop and move on to the question and answer last session. Yes, that works. Okay, glad it worked for Larry. So I have one question in the Google Doc, which is, what is the difference between the E4S base CUDA 22.05 and E4S CUDA 22.05? Now, what we have done is, in the container, we have over 100 packages installed, and the size of the container is large. It also has TensorFlow, PyTorch, and a number of other Python packages in the full-featured container. But you may not need all of those packages. You may want to create a custom compact container. Now, what would you need in such a compact container? You may need NVHPC, you may need CUDA, you may need CMake, and you may need just MPI and nothing else. So we have the base container images, which have just the bare bones runtime system with the CMake and MPitch. And then you can have the full featured container. So you can create your own custom container from the base images using Docker files, where you can specify the the container. Does that, so the base image is much smaller. That's correct. So there's another question, say E4S was built with a particular version of a compiler or Cray MPH version as an external package. Will there be any issues if that compiler version is removed from Perlmutter before E4S CL is not yet retired from the system? Now that's a very good question. Potentially there could be a problem with that, where the compiler is just disappears and you may have some dangling references. But if you are inside a container, we have all the compilers and MPI and other tools that are nailed down. So you will be able to use the same container later and you will have the full environment while just replacing the MPI. You were not using anything else except the MPI from the system. So if you wanted a stable environment, you could explore Shifter as an option where you just build your applications, you use the libraries from inside the container. You can even have your own SPAC in the home directory where you can read and write and then chain the two SPAC instances using the web page that I just pointed out earlier. And then you could have a stable environment where all the compilers are always there. And then you are still using the fast internode interconnect like we did with E4S CL. Does that answer your question?
So if users do an image, shift the image, that all can be under control. But what if users are using the formatters provided E4S/22.5 version, and that was built with a specific compiler version. And then we only, I think, have like 2 or 3 CPE versions that including, I mean, the lifetime of a CPE version that which includes a specific CCE version might be much shorter than the E4S, say 22.05 planned support duration of 1 or 2 years.
Yes, and you know,
potentially be a problem.
Ideally, I would like to say that if you were using GCC 1102 to compile the E4S, then I would really like to request NERSC not to delete that. And if they do, even make a symlink to a more or less compatible version that you have, there's a good chance that the ABI will work, and it may work with a compatible GCC that's close enough, but don't delete the whole path.
Yeah, we ran into this issue before. If you remove anything that's in the spec configuration, in particular in the package preference, things that point with modules or prefixes, and if they don't exist, spec's not going to behave properly. It's expecting those files in the file system.
And in general, we should try and keep the compilers at least around for a while.
Yeah. The spec YAML file has a list of external packages. They usually are the current default version of these, including compiler, including say Cray, NetCDF, etc.
Yes.
There's a way that you can maybe save those software versions into global common instead of the OPT Cray directory. But I don't know if, say, that version from OPT Cray has been removed and you moved it to global common Cray NetCDF, for example, would you need to have to repopulate the E4S installation? Probably would, right? Because in all these symlinks and find where the software is.
Yes, but I would
problem.
I would suggest that if we are deleting something, point to a compatible version before deleting. I intend to keep all the packages that I showed in that paratools directory. I intend to keep it for several years. I don't intend to delete those E4S previous versions. So hopefully the NetCDF and other packages that I pointed to will remain persistent.
But these are system people decisions, like, or how many CPE versions we can keep live on our system. If there's a new upgrade, and the old versions may get removed unless we have a specific request into it. Say these versions was like, say you have production E4S versions every, say, half a year, then those critical packages and or the corresponding CPE version should not be removed. Because the E4S
that's
version,
right.
you have it for your plans 1 or 2 years support.
That's right.
Yeah.
Yeah, it would be very destructive if you remove at least the GCC compiler along with the cray pitch. If you can just keep those versions, but just add new cray pitches, that's fine. But if you start removing, then it becomes a significant work on rebuilding the whole stack, rewriting the spec configuration to map, and then you may get into other errors. Like an example is like, let's just say you remove CUDA toolkit, and then you get a new version. Then we're gonna have to update our spec configuration with the new CUDA, and then maybe some packages don't build with the new version, just even a minor update. But those are the problems that we've typically faced, like when we built E4S on Perlmutter.
Yes,
I mean, this is not Perlmutter, but any system that has these.
Yeah, especially if those compilers and things that the packages depend on are getting deleted. That could be a problem. Now, I should mention that SPAC can install NVHPC with different, CUDA versions inside the SPAC hierarchy. So even if the system versions disappear, you could still use that, like we do in the base container images. And containers are especially useful for the situation that you're describing, where the system admins delete the compilers, where the environment remains relatively stable with the shifter.
That's right. Thanks.
Any other question?
I just shared, if you're in the Slack channel, there is a link to the a form we just created just to give feedback. So I appreciate if you guys just take like a few minutes. It should just take maybe 2-3 minutes to just fill it out.
Do you want to also share it in the Zoom chat?
Oh yeah, that's a good point. Yeah, I'll do that in the Zoom chat also.
Everyone can take a minute.
And yeah, I think just like open up to anyone if you have kind of any feedback that you like to help improve this session. It would really help. If there's anything that you liked or you'd like to change, you can speak now.
I hope you found the session useful and were able to do some of the hands-on exercises that we put together. I just released 2 of the nodes I was using, so somebody else was not able to get the node. I hope you get it now.
I guess I have a question. I guess for those of you that are on the call, I guess, do any of you use E4S that's actually deployed on NERSC? And if so, how you guys using it? Is there any way we can help improve the support around E4S? If you don't use it, you can say no also, that's fine.
Well, we look forward to working with you. Please let us know how we can assist you. Any parting thoughts?
I guess I'm not hearing anyone else. Well, I guess I appreciate all of you guys sticking around and just and all the presenters that were here. And yeah, please fill out the survey and hopefully we'll see you guys soon. And have a nice day.
Thank you.
Thanks, Jose.